All right. Let's see. Got my music going in my head. Let's make sure everything's going. You're here in chat. I saw Mika was in there earlier. Say hey. So we got a couple of people already in. Good to go. All right. Let's see. What do I want to put on screen? What do y'all want on screen? I think I want this. What's up, everybody? It is Jason. Yeah, it's nice to see y'all back. Got the stream, the new camera set up. It is a wonderful Friday, and hopefully your week has been great. And yeah, today we're going to be talking about SIMOTION, one of probably the most like requested topic that I've had on here. Um, Hold on a second. Let me get my music down. It is a little too loud. All right. So so we're talking about SIMOTION today. And it's probably one of the most, like I said, talked about requested topics because it is quite a special topic. But before we get started, I introduce myself. Most of y'all probably know me. If you're new to the stream, my name's Jason Watts. I have the founder and CEO of a little company, automation company called Alpha Industrial Technologies. Born and raised in Alabama. That's where the company's our shop is. But I live here in Atlanta. Here I'm streaming from West Midtown warehouse. So if you hear people actually working, that's because yeah, they're working. Like probably I don't know, probably not like you. Hopefully y'all are already off work. You're coming in from work from a long day, um, just kind of eating some dinner, popping open your favorite YouTube streamer. Well, I say that Hegamurl is back, and so yeah, I guess now that he's streaming, this is I'm your second favorite automation YouTube streamer, right? Uh, anyway, yeah. So we've got a fun set of stuff that we're going through today. By fun, I mean I don't know. If you find if you find this stuff fun, you're weird like me. But I'm glad you're here. And so as we get started, we're going to be talking about again about SIMOTION and kind of this broad scope of like how what SIMOTION is. It, it's a lot, and I will go ahead and say that as we are kind of like getting into this, I'm going to be comparing it a lot to the 1500T, which you see a lot on kind of the rest of this channel, because frankly, I mean, yeah, we'll talk about that. I won't ruin too much. Just a couple little things as we before we get started and really get into the stuff. You can kind of skip ahead if you're watching it on demand. Um, this session, there is going to be some stuff that kind of react videos and off-topic stuff after it, but I'm going to go through all of the SIMOTION topics, and if you have questions, drop them in the chat. I will answer them in that bonus time. That bonus time, no matter what, will always be available to the members. I've been talking to ChatGPT, and it's been making some suggestions about how to grow this channel. But yeah, one of those things is taking out all of the live stream and then clipping it out into individual videos and re-uploading them as videos. And I'm probably going to start doing that. When I start doing that, I'll be taking down the full VODs. But I'm like, all right, I'll make the VODs always available to members no matter what. So we do have memberships that a couple of different levels. The just kind of I think it's like a $2 level. You get the access to all of the extra content, all the extra videos, and if we're making data types and things like that, that I'll make those available to you in an archive. That one kind of doesn't get updated quite as much just because we use a lot of the same archive, or we use a lot of the same data types and things that we make. So um, yeah, and then the second level is membership. I think it's like $5, I think, or something like that. But um, you will actually get the archives for what we do today. So if you have a SIMOTION license, if you have that, you can open up those archives. You can play around with them. You can learn. And yeah, those are available to that programmer level membership. Got a bunch of other stuff in there too. But the free way to support this is liking the stream whenever you're coming in and subscribing if you're not subscribed. So we're gonna get going. We're gonna get moving. Hopefully, we got a couple of people in chat, y'all. I see Mika. Mika is here. He's like the like steady state of all streams. Like I see him in or I see them in uh, all of the different streams, including Hegamurl, which I I was on his stream this past week and or earlier this week, and I'm like, I'm gonna react to this, and later on in that bonus time, we're gonna react. So if that's still there, zoom ahead and watch that react if you're not really here for some motion content, but hopefully you are, because that's what we're doing. So let's get going and let let's start talking just a little bit about SIMOTION. And I'm gonna just a broad general overview of the SIMOTION platform. There's really three different flavors of SIMOTION. You have SIMOTION D, which is drives based, SIMOTION SIMOTION C, which is a controller based, which is it. I mean, it is a 300 series T processor with some special stuff going on, and then you have the P based, which is a PLC based, so not a PLC, PC based. So it's kind of like an IPC virtual style controller. So, oh, before I get started, one thing, the music is in my ears, but not yours, because I found out that YouTube released a translation, like an AI translation. So if you're watching this in India, the reason we're not doing, the reason I don't have any music or anything on it is so that that translation can actually process my voice, and you should actually be able to get Hindi dubbed content. So I know I've got a lot of Indian viewers out there. Hopefully it will be able to interpret my redneck voice, and you'll be able to kind of have a little bit of easier access into this content. So all of that to say, all my music was going, so it's like I forget that you can't hear it. And I also get scared of like copyright strikes, because the music that's in here is definitely not the little copyright free music that's on YouTube. But anyway, so I never get distracted, by the way. So I'll get back on topic. SIMOTION D, SIMOTION C, and SIMOTION P. Three different flavors, and we're mainly going to be talking about the SIMOTION D because we're drives people, right? That's what we're here for. But the difference between kind of the three platforms is the SIMOTION D has a built-in CU320-2. So it is kind of inherently based around the S120 hardware. Whereas the other two, not so much. They're kind of more like a T CPU, 1500 T CPU. In fact, the SIMOTION C is a 300T CPU. I think it's a 317 and then like a 319T. So like it's got two different flavors. I may be wrong. It might just be the 319. But the reason I bring this up is because, at least in the US, and I don't know how the kind of the rest of the world is, SIMOTION is actually entering into the phase out sequence, series, or phase out product life cycle. So that means that from this date, there's kind of an end date for the product. And I think it just went into PM400 this October, so October 1st. If you don't know, Siemens has their fiscal year is October 1st, and so they're kind of a quarter behind. So they released kind of all of their updates, their products and everything, kind of try to do it around that October 1st. So SIMOTION D is officially a mature, or SIMOTION period is it's officially a mature product, which means you're like, oh my goodness, so all of this stuff is going away. Yeah, it is. It's going to be at least 10 years from this date that there will be product support. So back in 2035, there will be product support for the SIMOTION platform as is. It just means that they may not be making updates. At some points, they will stop producing spare parts. They will stop mainline production, things like that. And the reason that they are doing this is because the purpose that SIMOTION had originally is not really needed. the processing power that was in the SIMOTION platform and the ability to synchronize the bus. When SIMOTION came out originally, it was not available kind of across the board. And so you had basically 3 different levels of motion control. You had your standard kind of PLC based EPOS, speed controller, things like that. Then you had your T processors, which were, I mean, they were pretty good. You had a lot of these motion control functionalities, you had gearing, but they considered those medium performance processors. The performance was, it just wasn't quite there. And then you had the SIMOTION platform, which was the true synchronized motion. That's what you see on all of this, like printing presses and kind of these really, really, really tight and like really highly sensitive motion control applications. Well, the biggest thing that was around at that point, and the reason why SIMOTION had it, and we're going to go into it and talk about it, is the integrated Profibus. So it had a high-speed synchronized Profibus network that was kind of synchronizing everything. Well, now you have Profinet IRT. And so with Profinet IRT, isochronous real time, that synchronous bus over Profinet is there. So I'm watching y'all come into chat. It's welcome into chat, and yeah, I see some familiar faces. And Ali Reza, like, great to see you. And by the way, Ali Reza, I saw your comments on Hegamurl's stream and so just so you know, I'm not looking. Like, it hurts my heart. No, I know. I know you love him more than me. It's okay. But guess what? Who's doing the SIMOTION stream that you asked for? Just remember, Ali Reza. So we've got some really cool long-time chatters in here. Like I said, if you're looking in chat and you see those when you kind of see the little different emblems and everything. Mika is one of our longest members here. I think that's over a year is that gold star, or not the gold star, the orange star. So it's awesome to that. So as we're kind of going through, I will kind of go through a topic, answer a little bit of stuff in chat, and we kind of go from there. And if you are in chat and you're kind of like talking, this is a community. And so we want you talking back and forth and kind of chatting. Like, for example, we got a question about which book I should read for motion. I mean, frankly, I didn't learn motion from a book. I learned motion from my dad and experience, which, by the way, my dad wrote a book and a lot about motion and a lot of different things. His is more his book series that I don't know if it's linked in this description, but it is linked on my channel. But those are a good book series that gets you started. It's not specifically about motion. It is a lot about VFDs, drives, PLC technologies, kind of that general, I know a little bit and I want to move up to the next level, or I've been working with this stuff for a long time and I want to kind of learn the nitty gritties, the kind of like deep down stuff. That's what that book series is about, and check it out on my channel. If not, I'll link it in the description after this. So, but yeah, that's written by my dad. And if I have any experience, he has 5-6 times the experience that I have, maybe 10 times. And so that's where that stuff's come from. But anyway, we're kind of getting back to this. The reason why SIMOTION was necessary was because of this synchronous bus that it has, and we're going to talk about it. But you have that now in the isochronous real time, so Profinet IRT. So now the 1500T is pretty much the same ability, especially at the higher end. So like the 1517, 1518 processor, those T processors are just as fast as the SIMOTION processor. And the tools that you have in that is a little bit easier to work through. But we're going to be going through, and I'm going to be showing you the old SIMOTION platform. I say old SIMOTION. it's the current SIMOTION platform. It's going to be around for a while. They just went PM400 on it a month ago. So it's going to be around a while. There's still a ton of systems. There will be a ton of systems out there that have it on there. And so that's what we're going through today. The first thing I want to do is flip over, and we're going to start up and talk a little bit about the software packages. So originally, the software package was Scout. So SCOUT. So SIMOTION Scout. Yeah, so Teddy also mentions in the thing the somatic drive controller. So one thing about the somatic drive controller, and I mean, thank you for bringing that up, because like I totally forgot about the somatic drive controller, because what it is literally a 1500T inside the package of kind of the SIMOTION D package, because I didn't bring in my SIMOTION D controller, but the SIMOTION D controller is essentially a really big CU320-2. Lucid, don't worry, you just missed the intro and all the important stuff, and me talking about how everybody has been watching the Hegamurl streams. So yeah, so perfect timing, Lucid. But yeah, the somatic drive controller is a 1500T packed into the form factor of a CU320-2. So it is kind of the highest and newest hardware in terms of the 1500T is the somatic drive controller, because they repackaged all of this CU320 functionality into this the drive controller. So the old software that before TIA Portal, before anything, it was its own software package called Scout, SIMOTION Scout. And in it, because SIMOTION is a full automation system platform, it's not just a motion controller. It's not just for motion and drives. You can run an entire line, an entire plant off of a SIMOTION controller, because it is just a PLC with a high-speed synchronized bus to drive controllers. Inside the SIMOTION D, it's all CU320-2, so it's all that S120 hardware. And so that Scout package, for the longest time, when you had TIA Portal, which, I mean, let's be real, TIA Portal was absolute dumpster fire when it came out. Let's be real. Like, if those of us that remember version 10.5 remember that you couldn't even save fast enough before it would be crashing sometimes. So it was rough. It was rough, chat. But now, since TIA Portal is so much better, like it is excellent, they have brought that SIMOTION platform into the portal, because SIMOTION used to be kind of like Somatic Manager. You had your HMI integrations, you had all of that stuff. Yeah, we don't talk about Portal 10.5. It's just like Bruno. Bruno is TIA Portal 10.5. But you had all the HMI integrations, all the drive integrations, all of that kind of in Scout. It just didn't work very well in terms of like productivity. And we'll talk about that and talk about the differences, because you know how like in TIA Portal, you have your drag and drop capabilities of dragging tags onto the HMI, being able to pull up in your detail view and kind of dragging stuff around and really easily fully integrating everything into a single project, not just a project file, but actually having everything being able to work together in a project. Well, this version that we're going to be working with is what is called Scout in TIA. And it is SIMOTION Scout integrated into the TIA environment. And it's kind of a halfway stopgap point. I mean, let's be real. Here in a second, I'm going to open up the SIMOTION configuration that you see here on screen. I'm going to open this up, and guess what? It's Scout. Basically, the only thing that it really did was it took the tags and actually integrated those tags natively into Portal so that you could pass information back and forth between your HMIs, your different connections. Maybe you have some other Portal processors, something like that. It brings it into the Portal environment. There was kind of a stopgap in the original kind of versions of Portal where, what was it called? It was called a device proxy. And essentially what you would do is you would publish all of your 300 series tags, which the SIMOTION platform is based off of those 300 series processors. It would just export those into essentially kind of a plug-in to where Portal could actually have access to those things. And it was really kludgy. You had to export. It was bad. So this is Scout in TIA. So this is SIMOTION in TIA, and it works really well. And I was actually playing around, and this is the first time that I've started playing around with it, and it's pretty good. And the only reason that I was even playing around with it in the first place is because I had a customer that had worked with literally 10 years ago almost to get a system working and get them up to speed on Scout. And so I had a lot of experience with the S120s. I had a lot of experience with motion and all of this stuff. And so I was like, okay, tell you what, instead of you having to go through and take 3 or 4 classes to get up to speed on just the basics to where we can start talking about SIMOTION, I'm going to go take the hardest SIMOTION class and dive into this and then sit down over the course of 3 days and just one-on-one get you up to speed on everything you know. And so guess what? 10 years later, that system is now being upgraded, and they've taken this system and just run with it. And they've done an amazing job with just going through and taking what I was able to teach them in 3 days and really taking it to the next level. And so I've gone back in and said, okay, how do we take this into the 1500T? How do we need to go to this? And so that's really kind of the only reason I've gotten back into the SIMOTION for this, is just because it's like, all right, they're moving and migrating into the 1500T. And so I'm kind of helping them out in that. So what I've done is I have a 21-day license that you could go out and download. If you have your version of Portal, you just need whatever version of Portal, and then there will be a SIMOTION Scout in TIA for that version. I'm using version 17 just because that's what they were using. And then you can download a version, you can, not download, you can activate a license for the Scout that is a 21-day license. And that is what I've done. I've got 14 days on, I've got 14 days left on it. And so that's why we're doing this stream this week. So Ali Reza, you can thank my customers for finally making this stream possible for you. But so you can do this exact thing on trials. And again, if you're a member, you get access to this file. And if you can open the archive, then it'll probably say, hey, you don't have this package, this Scout in TIA package. So you download it from the support website, activate the trial license, and then you'll be able to open this thing up. So TCPUs have been upgraded enormously. Yeah. Oh yeah. And the G2, 1200 G2 is yeah, Teddy's in here kind of talking about the new technology. New technology is just light years above where it is, because you have like multi-core processors that are that have been in like the TCPUs for so long, and they haven't even really been using them. They've only been using the other stuff. So look at that. SIMOTION Scout. Oh, it's behind my head. Look. Oh, you missed it. I just got a little pop-up that said your license expires in 14 days. Just what we were talking about. So let's go through. And the first thing you're going to do is, again, we're talking about the SIMOTION D platform, all integrated into, and it has this integrated platform. When you have the SIMOTION in TIA, in your hardware catalog, you will have under your controllers, you'll have your 1200, 1500 somatic drive controller. There you go, Teddy, right there. 300s, 400s. Well, when you install this when you install the package um, for the Scout and Tia, you get this SIMOTION, and then it has all of your different options. So I've just thrown in a D435 here, and because, well, that's also my customer, what they're using. So yeah. And so I've thrown that in there, and I want to show one thing that I'm sorry for constantly, my nose is a little itchy. You've got some allergies, some dust and smells and stuff here in this shared space or warehouse is making my nose go crazy. But what we've got here, when we bring this in, this technically is the entire automation system. It brings in a 300T CPU, the PLC, and because this actually, the default name on it is PLC1. So it's coming in as a 300 series processor and what is called Dynamics Integrated. And that is a CU320-2, all built into this one SIMOTION D platform. And that's really all we need to do for right now, because you don't have to integrate in the communication between the controller and that CU320. We don't have to do that. I'm going to talk later about if you have to use what's called a numeric expansion, or I guess it's not a numeric expansion. That's NX is on the SINumeric. It's the CX module, or the CS32. Yeah, CX32. The controller extensions, because CU320-2s can only do 6 servo or vector axes. So if you need more than 6, which these controllers could do absolutely more than 6 axes of motion, then you're going to need more processing power. You're going to need more CUs. And inside this SIMOTION platform, it doesn't use the CU320-2. It uses the CX32 module. And we'll talk about that a little bit. Actually, let's go ahead and talk about it. So if you need to extend that, you're just going to drag one of these in. And when you do that, you have your CX module. And then when you go to assign to your controller, this looks very different than what it would be assigning like a Profinet device to a tCPU. And that is because this CX module does, remember that isochronous, that synchronized bus is Profibus. It's kind of like behind the scenes going on in this controller. So what these CX modules actually do is they hijack a drive click port, and then you're using the drive click port to kind of extend this high-speed bus. And so that's what this is about, what's on the screen right now. So you could just, if you're setting stuff from scratch, you could just say okay, and it'll bring this in. Now, I'm going to go ahead and save this. Now, let's look at the SIMOTION platform. Normally, you would just double-click on this. I've already opened it up because I wanted to make sure it didn't crash my computer. But here's what we have. And this, to kind of like the old school Siemens engineers, this looks very familiar. This looks like Starter, because guess what? It is built off of Starter. And the big difference is because it has all of this other stuff in it, it has everything that Starter can do in terms of drive functionality for the S120s and things like that. Then it has all of this motion control processor functionality, and we're going to be going through all of that stuff. So take a little bit of a break, catch my breath. How y'all doing, chat? Y'all doing all right? Because probably want to take in a deep breath, in through the nose, out through the mouth. Get that kind of like power breathing going. Yeah, Sean, awesome. Yes, thank you so much for all of y'all that have bought my dad's books. Yeah, my name is on those, and I helped him a lot, or helped him some in all of that. But those books are kind of like all of like a download of my dad's kind of knowledge out of his brain. He retired, got bored, and wrote a series of books. So yeah, that's what he did. So maybe one day that's what I'll do. Maybe I'll write a book about about things. I don't know. Uh, but yeah. So all of you that have bought those books, thank you so much. Like it every time I see kind of like the purchases that are going through, I'm telling my dad, I'm like, hey, look, you're getting some more, because he's like, he doesn't really necessarily want like the revenue from it. That's why we kind of try to price them as kind of like reasonably as possible. But he's just like, oh yeah, just put that forward. But every time I tell him about all the people that y'all are like buying those books and everything, it just makes him smile. He's like, there's people all over the world reading his books and learning from him. And so thank y'all so much for that. Like y'all make my dad's day like every time. So thank y'all. Uh, and so yeah, let's get back into SIMOTION. And I hope that that vacuuming or whatever that sound is back there isn't too loud. Like I said, people doing actual work. It makes it sound like I'm part of something bigger, but yeah. Oh, all right, Ollie, that's awesome. Which yeah, I definitely need to make sure I know, keep track of Ali Reza, like who he is. Ali Reza was like one of the first commenters on my streams when I started doing these, so I definitely remember people. So first thing we got to do is set up our S120, because what is motion without drives? So if you're familiar with the S120 setup, and if you've ever done anything inside of Starter, then you will be very familiar with this kind of setup. So you come in and you'll open up SIMOTION Scout into TIA, and you'll notice two different things. One, you have the Dynamics integrated highlighted here, and then there's the CX module that we put in earlier. Now, both of these are CU320-2, so they operate, it's set up, they work just the same. They even have the drive click ports, kind of all of the stuff that you would kind of expect from a CU320-2. It's just this one is built into our drive. So let's just go through and just real quick, I'm just going to set up one axis a piece, just to kind of like step through the different things. So a little bit about, so if you've never set up from scratch an S120 system, you need to know that S120s are kind of inherently designed to be on a common DC bus system. So you have a rectifier, which Siemens calls infeeds, and then you have motor modules. So you have a rectifier section, infeed, then you have your motor modules. Some people call those motor modules drives. Some people call them inverters, because a drive, normally you have AC coming in and then variable frequency AC coming out. And so that's a drive. With an S120 lineup, you're going to have some sort of rectifier, either a basic line module, a smart line module, or an active line module. It's going to create a DC link, and then you're going to have motor modules hanging off of that, and then that's going to be what you connect your motors up to. And those motor modules are just inverters, so DC to AC inverters. So some of this stuff, we're going to configure a drive unit, which is kind of the whole system, and then we're going to kind of go from there. So we don't have any option modules, a drive with a drive, and optionally with an infeed. Are you using a Dynamics infeed with drive click connection in the drive unit? Yeah, sure. Yeah, because we like active line modules, because we're nice. I'm gonna select the 16 kW unit that I got back here. We're in the US, so we're 480. We like more power. Oh. Okay, so got that. What is that? Supply is standard. That's the controller connection. We configure power unit, motor. So yeah, so we've got a servo drive. We're going to select the technology that, and if you notice this is combining a bunch of those kind of the wizards that you would normally do. Normally you would set up your in-feed by a wizard. You would set up a drive, a motor module by a wizard. Well, these are kind of combining all of those into those one things. So we're just going to do this speed control with encoder. We're just going to click through these. It's servo. Sure, we've got, these are usually the ones. Yeah, so this is the new one. So we've got the 080. So this is a new hardware, new-ish. Sure, we're going to have, we want US units because we're in the US. I should do this because probably at least half, if not more, of my of you guys are not in the US. But for this, we're going to just use a drive click motor, like a 1FK7, 1FT7, something like that. 1PH8 with a drive click. We're just going to click next. Obviously, all of this stuff is offline, so you're not going to, I'm not going to be able to kind of show you online how to tune things. This is just the introduction, showing you how to set stuff up. And a vacuum cleaner is annoying. So let's just click through all of these and get through. Encoders, again, this is exactly the same as you would be inside of Starter, S120, kind of the same wizard that you've done. If you've done these once, you've done it many times. So kind of go from there. We're going to finish that. And then now we're going to have a in-feed and a drive. And that's really what we need. And we can go through, and just like in any sort of starter, we could go through at this point and use this to tune and get our motors in sync, get them going like as they should. So hopefully you're not writing your code on site. Hopefully you're going through and setting this stuff up ahead of time, and then going and writing all your code, doing all that stuff, testing, doing all of that, and then going through on site, doing the commissioning. But that's basically what we have here. All right. So far, this shouldn't be anything out of the ordinary. It might be something new to you because you might be new to this channel. You might be new to Siemens. Welcome. If you haven't liked the video so far, smash that like. And if you're interested in this content, be sure to subscribe. Back to your regularly scheduled stuff, you know, all the YouTube things. But so that's basically all we really need to do right now for our axis. Obviously, that can get complicated if you have special motors, encoders, things like that. Again, this is just introductory, get you to know how to the work process flow for this. So the next thing that we want to do, and this should look pretty familiar to you in terms of kind of using the technology object principle, is we're going to create an axis. And what an axis is not the hardware connection, not a drive connection, even though you kind of want that, that's down here. You have this software that has all of these settings, all of these features, all of these kind of like position data, functions, like all of these things over here that you can connect software to, but it's not necessarily the hardware. It's almost like you have a set of software that doesn't change, but your hardware does. And if you're familiar with that, that's a technology object. So if you're kind of picking up on things, not only is this a TCPU, but this is really kind of the concept of technology objects. And I've talked about this in other streams, talking about the technology objects in particular, and that technology objects aren't necessarily new, but Siemens is the past, I don't know, it's probably been a decade now. I'm old. But the past 10 years or so, they've really been focusing on trying to bring this concept into kind of general motion because it makes for really modular code. And you're going to see that here in a second when we get to this stuff, because you have an axis that if you have that type of axis sitting over here, your code works, then what is down here at the hardware level, it doesn't really matter as long as it's set up properly inside this access or the axis. And that's the same thing with technology objects. So let's go ahead and we're going to set up an axis here. Let's just call it feed axis. Okay, and we are going to want to engage this onto, so yeah, make sure that you can see those, because the different options here in technology objects, you select a different technology object type. So if you want to be able to do any synchronous option, or like camming, gearing, kinematics, anything like that, you need to have a synchronous option. And that's a technology object of a sync axis, a synchronous axis. Well, in the SIMOTION world, everything's an axis. Then you select the capabilities inside this little box here. If you're just needing speed control and you're wanting to control, everything has to be connected to an axis. Remember that. So if you're just running a fan at a speed control, it needs an axis. If you're running a positioner, just a simple back and forth positioner, you need an axis. If you're running some sort of kinematic thing over here, it needs an axis. Not necessarily the same thing in the 1500T world. You may or may not know that you don't have to use technology objects in order to run a pump or a fan, something like that. You can absolutely go through and use something like SINOSpeed or SINOPause and run some lower level motion control on this side, and then use your technology objects, your synchronous operations for things like electronic gearing, camming, kinematics, those things over there. Technically, you could do that in SIMOTION. Most people did not do it because it was just, why would you? You have the extra horsepower to do this axis thing. So the last one here, though, is path interpolation. So anything that you need to, like kinematics, for example, that's a path interpolation. So you're needing to take multiple axes, and you're going to take those path axes and tie them into this path object. That is a little bit different from a technology object. Technology object, you take synchronous axes, and then you have a separate path object, a kinematic technology object, and then you point essentially these three axes, or whatever your kinematic axes are, up at this. So you point them up to the kinematic. A little bit different. So anyway, we want synchronous operation just because we're going to gear this thing onto a master axis, a virtual axis. So let's go through and again talk about these things here. Linear versus rotary. One of the things that it calls out really well in the technology objects that it doesn't necessarily show here is the unit type. So in a linear axis, your units are going to be in millimeters, they're going to be in linear units, millimeters, inches, feet, miles, kilometers, whatever, something linear, distance. Whereas rotary, it's going to be in degrees or radians. So degrees per second squared. And there's a reason why you would pick one or the other. And like, yeah, I talk about those ad nauseum in some of the technology object streams, and those concepts are the same thing here. Sometimes you'll want to measure things out like a roll, like a sheet of paper. You're gonna probably want to do a linear axis for that thing that's measuring it. But you'll find that sometimes it's like, oh, my math works a little better if I do that in degrees, and then just convert the degrees to a linear unit based on the size of the roll. So just know that there are some times when you would go back and forth, And just because it's a roll doesn't mean that it's going to be a rotary axis. Sometimes that roll is measuring out a linear distance. A lot of times people think, oh, it's on a ball screw. That's a linear axis. That's okay. And then anything on a roll would be rotary. That's not the case. So we're just going to do a linear, and this is going to be electrical. If you notice here, in a second, we're going to click this virtual button. We've done this before. Watch the Motion 102 stream where I actually go through in the technology objects and set up on my demo unit back here, set up a cam, and it actually is going back and forth. And the only way that I can do that is by using a virtual axis. Same concept here. Again, this is kind of the grandfather of the modern day technology objects. Same thing, just the same thing as a in the technology object. You have to point that axis. A real axis has to have a real drive. You can absolutely skip over this if you want to just program it without an assignment. You can click here and then just say like you can unassign this. Yeah. Well, I thought you could. Anyway, if you don't have those motors set up, it definitely allows you to continue on and set up your axes. And so you can do all of that and go back behind it. I'm just not necessarily familiar enough with this to do this. So here's this thing, a standard motor and a linear motor. Those are big differences in technology. Standard motor, it turns. Yes, this is a fancy permanent magnet servo motor, but this is a standard motor because it has a shaft that turns. A linear motor is not this. It's essentially you have loops of wire in rails, and then you have like a magnetic trolley that runs across it. That is what this means. Is a linear axis is a physical linear axis. They're stinking cool. They are so stinking cool, but they are expensive, really expensive. But so most of the time you're going to be using standard motors, even if you have like a ball screw set up to where you're doing linear motion, but it's a motor that's turning a ball screw. That's a standard motor. This is not the linear that from before. Yeah, so the encoder. So you might actually have external encoders, and we have some here, like over on this left-hand side, over here. You could set up an external encoder because sometimes you'll actually, there's either play, backlash, something in the mechanical system, and you want to have a guaranteed kind of closed loop on the position. To close the loop on the position, you don't necessarily want that to be on the motor, because there could be other things that is out on the position, which we'll talk about this. Remind me to talk about this when we're reacting to Hegamurl stream in the bonus time, because I'm gonna write this down because I want to. This just popped into my head. By the way, this is mostly just off the cuff, just stream sort of stuff. So yeah. Because what I want to talk about in that stream has to do with linear resonance and things like that. And that's some of the stuff that closing the loop with an external encoder will actually help in terms of an internal encoder. Because your internal encoder can only measure so much. Your external encoder is the actual end of the process. We got a question here. It says, hey, do you have any idea about synchronization in S110 using starter software currently? We have to use this task. There's no way to do it in the drive itself. So So we got a question about whether or not we can do syncing in the S120 itself. So in the old master drives, I assume that you're younger than me, and so there's no reason you would know this. Okay, so in the old master drives, which was the series before the S120s, they had all of these motion control functions like actual electronic gearing built into these blocks called the FO1 blocks, F01. And they were really powerful. And if you bought an MC version of the controller card, then you got these functions. In the S120, they took those out and everybody freaked out because everybody was upset because, like, look, you're taking a step back by taking away this motion control functionality. And one of the things was the every it was a processor thing. Well, later on, Siemens did come out with Siemens did come out with a package called GMC gearing, General Motion Control Gearing. And I've talked about this a little bit. Actually, I have a whole nother stream about DCCs, DCC charts. And DCC charts are a package that's built into the S120 to where you can actually load in function block diagram. You can load in extra functions onto the S120. Siemens has a free package called GMC, so the GMC library that you can download and put onto that can gear up to 3 axes of motion with electronic gearing built into the S120. This is not a very common application, but it absolutely is there. I'll tell you how uncommon the application is. When I was being certified as a Siemens kind of higher level certified S120, so a motion certified engineer at my previous employment, that was what we had to do. We had to set up a system with GMC gearing. So it is a pretty technical way, to do that. But it absolutely is there. If you're familiar with the function block diagrams and the function charts, yeah. So that is there, but it is not nearly as easy as gearing with technology objects for sure. So I don't think I mentioned this, but we do have a Discord channel, and honestly, that is the best way to get in touch with me. I prowl around on there all the time. If you type a question in the automation channel or the help desk channel, and there's an off-topic channel to talk about 3D printing and stuff too, but not only am I on there a good bit, but you have people like Lucid that has a lot of experience with Siemens as well. We even have some Siemens professionals in there that actually work for Siemens that shall remain unnamed that are also in there kind of lurking in the background. And so check out that Discord link. I think it's a link in the description of this. I think I do have that there. And it's should be in the channel. Let me make sure that channel description. Well, I can't see it here. It is in the description though, to where you can log into that and join into the Discord channel or the Discord server. And I'm on there all the time, answer questions. I was actually just before this answering a question about a poll ID function for the for kind of a one of these motors here. And so I was doing that right before this stream. So yeah, there is a link in the description of this stream, so you should be able to join there. So we've got to finish up our axis assignment, and that's basically it. So now what we have is the core part of a SIMOTION system. So we have our drive system is set up, and then we have our axes linked into the drive system itself. So now from there, we could start writing our programs. Just again, what we need to do, again, going back and comparing it to the technology objects in the 1500T, you're going to have to sit there and start the motor up. You're going to have to kind of home it. You're going to have to do all of these things. Hold on just one second. I've got my hold on, but my wife just called me, and I didn't know if she knew I was streaming or not. Need to make sure. All right, looks like she's taken care of. So yeah, there's 3 languages that you could program, start, do all of these gearing and options and all of these things. And as Alireza has mentioned, MCC is kind of the streaming. Well, no. So like anybody that follows this channel knows that I do not get in trouble for streaming too much. I need to stream more. At least YouTube tells me that. But yeah, so there's 3 different programming languages that you'll run across in the SIMOTION platform. And one is your good old ladder logic. Actually, hold up. There's 5. There's 5. So there's ladder logic, which we'll talk about how that's probably not what you want to do, even though it's available. There's ladder logic, there's MCC charts that Alireza mentioned, there's ST, but then there's function block diagram, which is kind of like available, like I don't even know if anybody uses that anymore. And then there's DCC charts. So there's 5 different languages that could be in one of these controllers, which is a little annoying, but sure. Most people, however, is kind of like Alireza, I wouldn't call them the lazy ones. It's the ones that don't necessarily want to work as hard to do the same thing, because the motion control charts, let's pull this up. Let's pull up because here in this little folder here, okay, you have all of your different programs. And the way this works is, you can see I've got a couple of programs already written here, and they are not written in any of these other languages. They are written in ST. So we're not going to go into those right now. We're going to talk about ST here in a second. But MCC, these are units. And one of the things to notice is that when you click on these, this isn't necessarily it is one file, but it's not necessarily one program, one function, one thing. So like the only way I could kind of relate it to in the technology object world is you can define a bunch of function blocks inside one file. And so whereas in technology objects, in your kind of like regular programming, you define a function block, you say create new function block, and it says, okay, what language do you want to write it in? Okay, I want to write it in ladder. I want to write it in SCL. I want to write it in STL. Then you write your program, and then you're using that function block somewhere. That's not necessarily how it is. You have these source files for ST, you have MCC units, and then you have ladder function block diagram units. And the units are essentially, you make this group that then you can add in for motion control charts. You'll add your unit, and then you'll add in your different charts. For function block diagram, or for your ladder, you'll add in kind of an overall ladder, and then you'll have all of your different functions that are defined in there, like your function blocks and things like that. With ST, you can write all that in one file, and we're really going to go into it because that is the really powerful tool and really powerful way that SIMOTION works, and is honestly why a lot of people use it, is because of the ST functionality. And just so you know, ST and SCL look very close, but they are very different. Or I guess they're not very different. Their syntax is very close, but functionally they work different because of kind of like the memory definitions that we're going to be utilizing in this program. So let's just insert an MCC unit, my MCCs, and what we'll see here is that now I have this little thing here, this my MCC unit. I now need to go in and actually insert an MCC chart. And the way MCC charts work, yes, so just so you know, we're kind of have a couple of different questions about the different languages. One of the reasons why I don't have the music is only in my ears and not on the channel, is so that we can do the Hindi and other languages, the conversion. And now sometimes it goes crazy and we'll say something that, like, the way that I say the word Siemens does not get translated to the company Siemens. It gets translated to a sailor on a boat. So pardon me if some of the different translations don't make sense, because yeah, I can't be, but they will be available for what they're worth. And what would be awesome is if there is some sort of like crazy translation that just makes you laugh, let's talk about it. Tell me about it on stream, because I would love to hear the differences between the two languages, because I know my redneck accent is going to be giving that like translator trouble. So we've inserted this MCC chart. We're just going to, let's just do my motor control. And I'm pretty sure I don't have to worry about this thing. It's a program. Because function block, yeah. So the creation type, so whether or not it is making something that you can call in your code, is a function block or a function. If it is a program, that has to be called by the execution system, which we're going to talk about later, because that's cool stuff. But anyways, we're going to make this a program, and we're going to open it up, and it is a chart. All right. So it's graphical. And so everything that you have on here is based on kind of like this flow chart. So you want to come in, and you have these toolboxes up at the top. You have your basic commands like if, then, else, actually, program structure. That's the one I want. So if we come in and let's just make a if branching. So you come in and you say, all right, if, then I can say a formula. If 1 equals 10, 1 equals 10, which that should be never, right? So that's always going to be false. Then I can come in and on this branch put in some sort of thing like enable my axis. So I want to enable my axis, switch axis enable on, then I'm double clicking, and then I'm going to select the axis for this. Very, very straightforward, very visual. And there's a reason why Ali Reza said that it's for lazy, because it's not that it's lazy, it's just because if you have just basic functionality, if then, here's when you want to start this, here's when you want to stop it, why would you not just click through and do it this way? And then that's how you do that. So, and then now, once that is finished, I can go through and add in like some sort of function like speed specification. So that means I'm going to run this axis at some speed. And then all you're doing is all of your settings for that function, you're setting up visually. Pretty straightforward, fairly simple, but you can explore all of these kind of settings and diagrams and everything on it. So in this one, here is how you would set your speed, and then you can select different variables, select different things here. And so, yeah, so last programmed, resultant velocity. So there's all sorts of stuff that you could do here. I think it's not showing up because I don't have variables that are available to this. But yeah, that's going to be what speed you run at, whatever that is. And then you go through, and dynamic response is going to be the ramp function for that function itself. So you set everything up there. And then I don't know what's over here in this expert. Hold on one second. So yeah, so we say okay there. So that's how motion control charts work, and they're fairly simple. And you can go through and do all of these. Apologize, but 20. All right. So moving on to that, again, my wife's texting me. I got to make sure she's taken care of. So, and next thing is the ladder editor. So I'll show you why you probably don't want to use the ladder editor. So let's go through and so let's my ladder. And now we can go through, and the same way that we did with the MCCs, we can do with the ladder functions. So, and again, the creation type, is this a program, a function block, or a function? And if you'll notice something, nowhere have you seen the ability to be able to create a data block. And that's something that's like very common and very much a thing that is like, oh, well, I need data blocks. And we're going to talk about that here in a second, because it's not as straightforward. And I don't quite understand why it's this way, but I understand how to get around it. So we're going to create a program, and we go into it. This looks exactly like your ladder editor in TIA, doesn't it? No, it doesn't. This is like some of the worst. This is quite possibly the worst ladder editor in the history of ladder editors. And it's like I can't even insert a network. it's horrible, guys, like, and gals, and yeah, it's rough. But yes, you can create ladder branches like that. All of this, none of it. So I'm going to tell you something about this ladder editor. I said that just a second ago that this was the worst that I've ever used. It's not. It's not. There is one that's worse. It's called TieSoft. And if anyone is used to or if anyone has ever used TieSoft on the old Siemens 505, like y'all just go ahead and like give like an '07 in chat, because good for you if you've used TieSoft. Yeah, this is second worst compared to that, because everything is just bad. You can use the functions and like all this stuff. You can make things. It's just everything about it is more difficult. Like your symbol table is in here. Like it's just a lot more difficult. And honestly, I don't see a lot of um I don't see a lot of people using this ladder editor, just because there's so much better options, namely ST and MCC. There's with MCC and ST, the only reason you would really want to use ladder logic in this is if you were taking like push buttons and starting functions, like with push buttons, IO, visually it can kind of go through and do that sort of stuff. Because if you're using ST, why are you going to try to build some sort of math function in ladder logic? No. If you're using MCC, why are you going to trigger MC functions in ladder? You're probably not. So about the only thing that you're going to be doing is like sequencing, kind of checking, all right, is this E stop here? Is this good? Those sorts of things in ladder. I'm going to leave this here. I don't ugh. Yeah, we're going to pretend that never happened. All right, chat. We're going to pretend that never happened, cuz it was rough. And apparently, so Sean's talking about the Mitsubishi ladder editor. I mean, I fortunately have never used the Mitsubishi ladder editor, apparently, because it's apparently horrible too. What's the Automation Direct processor? Not the Seymour. Is it Simplicity? Something like that. Anyway, it's pretty bad too. It's right up there with it. I mean, it's free, so you can't really complain if it's free, right? But we're gonna get into the real motion, real stuff now. Y'all ready? Because we're about to go into ST. And ST, my friend. By the way, the music. I'm listening to like EDM music, and it's like building up to the beat. ST. ST is where it's at, and you're going to see it mostly across the board. One thing, because it is so much more portable than any type of any language, anything that we have. And you have kind of these code assist processors, they use ST, all of this stuff. So like I can see why it's like it's text based, and so a lot of people are like coming from ladder and these visual languages. They come in and they have no experience in text-based stuff, and that's kind of how a lot of us old school, like gray-headed people like me, that's where we come from. Is all right, we're coming from the non-text based stuff. Not me specifically, but most of us. The youngins these days, and there's probably a lot of y'all in chat. The youngins, they like the text based stuff because they've been like raised on it, and it's really easy and really good. And I know Lucid probably will complain about some of the stuff that I put on some of his equipment, because I will randomly drop in like an SCL line in a bunch of ladder logic, and then I'm just like, oh, this sucks to be done in ladder logic, and then so I'll just make a network of SCL, do a bunch of text, and then just collapse it and hide it, and no one sees it until Lucid's like coming along trying to figure out what I did, and there you go. So ST is structured text, and it's some ISO defined language. But one of the things that ISO number, if y'all know what ISO specification ST is based off of, in chat, y'all toss that in chat, because like, yeah, that might be something good to know, because you can kind of cross-platform these different things if they meet that specification. You can take code out of one, and as long as the function calls and function blocks are defined in the code, then you can reuse that code across platforms, which should get you excited. So if you have some sort of like Lenza drive system, or I don't know if Alan Bradley has it, like I don't know if Kinetics has, or their motion control uses that ST, but any of these motion controllers that use ST, Delta V, anything that have ST, you can take that and you can write your ST in a way that you can take that off of this platform and then take it and put it over onto another platform, and then change a couple of variables, change a couple of interfaces, and then there you go, it's up and running. That's pretty stinking cool. But I'm not going to go into all of that. That's like tier 5 stuff. Like that's more of kind of like higher level programming stuff instead of just like your SIMOTION platform overview. I want to show you the basics of how to use it inside of SIMOTION, so that when you run across it in a SIMOTION project that you're coming behind, then you're not going to be like, what the crap is going on here? So first thing I want to show you, I talked about those data blocks, how there's no data blocks in SIMOTION, or at least you didn't see them, because technically I haven't found them. If you know of how to make if you know how to make a data block in SIMOTION, comment into it. Ali Reza probably, it looks like he has the most experience with SIMOTION. So Ali Reza, just comment if you can make a data block in SIMOTION. I haven't figured out how. The way that I do it, so you have your IO tables, and you have, so your symbol browser, where is it? Hold up. So you have your address list is kind of like your actual kind of IO. And so you can go through, and here I have like an input set up, and it's tied into I0.0. And so input 1 is I0.0. So you can go through and set up all your different IO. So inputs, outputs, I's, Q's, IWs, QWs, those things. You can set those up in this address list table here. Okay? That kind of sucks, because it's just doesn't feel right. Like, especially when you're used to every other system that I've used, and maybe it's just so old. It's the old way of doing it. You did this again on the 505 system. Like in TySoft, this is what you had to do. You had your IO tables that you had to set up. Why are we doing this? Anyway, end rant. A little bit better way of doing this, and honestly, kind of props to whoever kind of wrote this other some other code that I've been looking through, like in different places. There's some better ways to do it inside of the SIMOTION platform, that it's like, oh, this actually is pretty good, and it creates portable code to where you could take out and that we can take out and put into another device, and then kind of redefine what these tags are in terms of IO, and then we can just all of a sudden start using those functions. That's portable code. That is like the creme de la creme of programming, really. But especially in motion control, you do have a lot of different machines, different things, but most machines kind of fall into kind of similar things. You have torque control on an axis, you have speed control on an axis, you have gearing on this, you have camming on this. And so one flying saw to another, there's not going to be a lot of differences in the core program. It's just going to be in kind of all the stuff around it. So whether you're using that Alenza or a SIMOTION platform, if you're using ST and you set it up this way, it kind of works. So Mika asked if ST refers to the same ST in the PLC we know or SCL. So in Portal, so like on the 1500s, you have two languages that sound kind of like that. You have SCL, which is it's structured call list or something like that. That's the text-based language that looks kind of like what we're about to do. Then you have STL, which actually has ST, but that's statement list. And statement list is assembly language. It's like machine code. It's like hardware down. You're loading accumulator, transfer, add, accumulator to. It's rough. And if all of that stuff that I just said sounded like another language, you're probably under the age of 25. Like they don't teach that stuff kind of as much as they did back for old people like me. So ST in this is not STL. It is not SCL, which are the two languages that are in the 1500 and TIA Portal. SCL is very close. No, I'll talk about the difference. Let me just talk about the difference. So I'm going to go in first, and so I have this var global type or var global source file. And if you're not familiar with kind of text-based programming languages, you're going to have files, and kind of the goal would be to have a one file that has a bunch of stuff that you commonly use, and then you have another file that's custom stuff. And then you say, all right, I'm going to point and use all of this stuff, and then I'm going to have access to this. And then I can use whatever. And so as long as I have this file can run. So whenever I include anything, I just include both files to make sure that I have access to both files, and then I can run this file. Okay? So instead of having DBs, which in the PLC land, in kind of the 1500, you'll have a DB, and that'll be a global DB. And so that is access to information, access to data, anything, any program that is running, any function, anything can have access to that data. And you do have that. You do have global device variables right here. But again, they get down in this stupid like thing that's like right here to the side, like this little thing right here, right here. This sucks. Like it sucks. And that editor just it's cumbersome, it doesn't look good, and it's hard to kind of step through and trace through. And so what you normally will do is, instead of using this, or what I see a lot, I'll put it that way, is instead of using this global device variable and this address list, you split everything up into these global source files. And then you just include those in anything that needs those variables. And so in this global source file, let's talk real quick about an ST file, because this is kind of like the way that you can structure an ST file. Every ST file, every ST source file has two parts: an interface and an implementation. The main difference between SCL and ST is that SCL does not have an interface in the code. It is only implementation. So the interface is up in that kind of like higher level block area that's like all of your code sitting right down here, and then your block up at the very top. That's your interface. That's where you define inputs, outputs, static variables, things like that on whatever you're working with. That's up at the top, okay? Well, every ST file, it's just a piece of text. It's just a file. And so it has to have some way to define all of those inputs, outputs, whatever it needs, the same way that an SCL has that sitting up at the top. So my this variable, this is just my source file for my global variables. So inside this file, there is no implementation. So an ST file with no actual code in your implementation is just definitions. It is the equivalent of a data block. So this is the best way to write a data block in SIMOTION, is in these ST source files and have only an interface. And so, by the way, I'll show you something real quick. So the help files on SIMOTION have a where is it? It's programming in ST. So when you open up TIA in Scout in TIA, this kind of interface, it opens up this HTML help. You can hit F1, it brings this up, but kind of like burrow down. We're going to be using this here in a second. That's why I had it up. But there's a section called programming, and there's a ST programming language section in it, and it goes through highly detailed, very good. That's your ST book. Okay, if you're looking for a book to learn ST, here it is. It's included. It's in the help file because it literally goes through, has an ST fundamentals, and each one of these. So like, it's a class. It is a ton of information, and it is all in this help file. So I'm going to scrape just the very top of this just to introduce to you some of the basics so that when you're looking through someone else's program, you have an idea of what's going on. But programming, it's all in that. Yep, Lucid. This is Code Assist, and there's, I wouldn't call them, there's on LinkedIn, there's all these there's these people that love to talk about like Code Assist and all this stuff. And yeah, of course, being the Siemens guy, I know a lot of different Siemens people. And it was a funny story. I was at a conference called SPS just I guess it's probably about a month ago or so. And there's a Code Assist booth there, kind of right next to the big Siemens booth. It's kind of like a Hanover Messe style thing. And I was sitting there and I'd gone through and like shaking hands with all of like the Siemens guys. And I walk over to the like Code Assist booth and I start talking to them and I'm like, oh, okay, and start talking. And I could see my buddies from like over in the like Siemens group, and they're like, but yeah, Code Assist definitely has some great thoughts, but it is all based around ST. And so if you don't know this ST interface, and you're going to have to get used to this text-based programming language. So we have determined now that a ST source file with only things in the interface is the functional equivalent of a data block. And if you don't know what a data block is, go watch my video on the OB, FB, and DB, all the different letters that end in B. But for real, there is a ton of information about this that I put out. Hegamurl has done a bunch of stuff. Honestly, his stuff is a lot better than mine on the basic PLC stuff. But yeah, so let's talk about this. The kind of two things I really want to highlight, okay, is this keyword here, uses. So uses means in the equivalent of make sure to include everything in another file. So if you notice, this says uses my types. And if you look over here, there's this source file called my types. And again, this is just a way to kind of structure your program so that it actually makes sense and you can track everything. And I got to talk about good PLC structure, because if the king of PLC program structure, you should know, is PLC Skill Tree and Hans. And if you're not subscribed to that channel, you need to go and look at that, because he talks about how to structure your program to where it doesn't drive you crazy, and the person that's coming in behind you like doesn't want to throw eggs at you if they see you. And so check out PLC Skill Tree too. I'll give you that call out, Hans, because he helped me out on LinkedIn earlier today. But uses another file, uses another source file. That's what this means. And so everything in this my types source file is available to this file. And you see this in other text-based languages, C, C++, Python, all of that stuff. And so you might, I can't remember the keyword in, is it uses? Or no, it's include. Like if you're doing an Arduino, that's like pseudo C++. It's an include another file. And then that means you have access in yours to everything. So this uses my types, and in this, my types is just a bunch of definitions of structures. We'll talk about those in a second. But just know that you're kind of breaking up everything. In 1500T, in kind of like your normal programming environment inside of TIA, we talk about PLC data types. I've got a couple of streams that I talk about them. I've got a couple of videos, all this stuff. But PLC data types is the best way to take your programming to the next level. And it's not just here in SIMOTION. It's in your regular kind of TIA portal. So you're taking things that you use a lot, structuring it in a way to where everything is taken care of you. And then all of a sudden, where you could use the word like, all right, I create a variable and it's a type of Boolean. Well, here, because I have this data type defined, I have this blah, blah, blah. Yeah. So this line right here, if you notice here, the structure of how these are just defining variables. Okay, so you have variable name, colon, and then the type. So this variable, system update rate, is, I don't know what it's being used for, but it is of a type long real. Why is it a long real? Who knows? But then I'm setting it equal to 35.0. When you look at this is some sort of global constant. So we have on this line, we have a variable called myServoStatus, and it is of a type tServoStatus. That's not a bool, that's not a real, that's not a dent, that's not a time. That's my special type that I defined. It is a user-defined type, and that is what all of these things in here. I just have one. And if we look at it, it has all of this data that's kind of underneath it, and it's called a structure. Sometimes you'll see them called UDTs. But and yeah, so like this should very much, if you've ever used a text-based language like C++, something like that, you might actually fall in love with ST, and then you may go to well, I guess if you fall in love with ST, you can always use Semantic AX. Yeah, which, yeah, that stream might be coming soon as well. So let's go back over to our global variables and talk about how to structure this. So we're using my type, and then we have, if you notice this, we have our var global keywords here. And anything that's in blue, those are going to be keywords. So they're going to be data types. They're going to be some sort of like structure interface. It's built into the ST language. And I don't know if in this editor, if you could define like custom keywords and things, and like change the colors, but just know that here, when you see blue, that means it's special. So a global variable is going to be accessible outside of the scope of this. And inside of like, if you've only ever used TIA Portal or Semantic Manager, or kind of programmed as your language, then you're going to scope doesn't quite make sense. If you're coming from that C++ world, scope 100% makes sense. If you're coming from Python, scope makes sense, especially C++. C++, scope is so, when you first start out, I'm like getting a little trauma here. Just going out of scope can drive you crazy when you're first learning this. But just know that if you are defining things as a var global, anything that uses this can have access to it. If you have a private, you can actually have private data in ST, and it's not global. And that's one of the big differences between function blocks in regular like TIA, is the fact that like a function block, even though you have static that's defined inside of your function block, you have static memory that's part of that data block. Technically, anybody else can access that data. Anybody else can go in and say, hey, I want to read that. I want to look at that. Well, in normal programming languages, that violates a lot of principles. It's called encapsulation. And encapsulation is very important when you're trying to write actual modular code, because you don't want other stuff messing with your stuff. But function blocks, there's no real way of doing that inside of Portal. And that is one of the powerful things of ST, is you can actually have true encapsulation. You can have private data that even if I have this uses var global, if I have it labeled as private, then you can't access it. Even though you're using that source file, it's private. The private data is only available to the interface, or sorry, the implementation that is there in this. And like I said, that's kind of a programming topic that has nothing to do with SIMOTION. Look at what y'all got me off on. Good job, chat. You got me off on programming topics. But, so, we've got two different types. Well, actually, we've got three different types here that I want to show you. So we've got our var global constants, var global, and then var global retained. And that's the three different areas and types of variables that we're using in this. So constants, they don't change. You can't change them. So you define them here. They are set. If you use this and you use that constant, it just is. So like it replaces your word, your constant, with that value, and it never changes. Those are great things for like pi, for example. You wanted to make a 3.14 blah blah blah, all of that. I don't know pi. I don't know. But if you want to put that in out to 20 digits, you can put that in as a constant, and then you can just call pi as a constant. There are system constants that are defined, especially in like Portal. You'll see me using, like if I want to get a hardware identifier for some function, like if I'm trying to do like try to get like a telegram, so like a hardware ID for a telegram, I won't go and search for the number. I'll show you how to do that, but most of the time, because I've named my stuff appropriately, I know how to find that, because I could just start typing and it has created a system constant of the hardware ID for that thing. It's already created it for me based on the name that I use. And that's why I always tell you, name your hardware, name it properly. Don't use underscores because they're illegal Profinet characters. Thank you, Siemens. But use dashes, use caps, use things that make sense to where it's not just PLC, drive 1, drive 2. Make it to where you can use these system constants, and you'll find that it really speeds up your life and makes your life easier. So we've got these, that's a constant. A var global is just kind of like the comment says here, global, not retained. What is retained, you might ask? You old school, or I guess your Siemens veterans know the difference between retained and not retained, but retained means that if you power cycle, or you turn the machine off, it's going to keep that value. It's going to come back, and like if you put a setting in an HMI, we put a setting in HMI like startup timer or pause delay or some sort of shift or something. You want that to come back every time that the power comes on in your machine. You don't want to have to go through and retype in all of those variables every time you start your machine up. Well, those are retained variables. If it's not retained, then it'll stay between cycles, but after the power goes off, it comes back up, it's just going to be whatever its start value is. Retained variables are only overwritten when you reinitialize the data area that is. We'll say in TIA, in Portal, and on the 1500s, that's very much more well defined. I'm not exactly sure. I'm pretty sure that on the startup cycle, stuff is reinitialized in here. I'll have to check because I think I remember seeing something about that when I was studying for this thing. Yes, I had to study for it. But just know that normally retained is keeping your data. You want to have that. So inside of here, we have some global variables. Again, my type. So I've got my little servo, like my servo status for my axis. And then I've got a couple of input, like my part present, my home procs, output, my air solenoid outputs, my warning alarm output, just some variables that I'm going to show you why I'm doing this here in a second. Because what I'm setting up is for my program, anything globally that I need, I'm going to define it in this. And so I can use my global variables in anywhere. Okay. And you're like, all right, why do I keep this? It shows up later. Same thing. So with retained, maybe I need some HMI stuff. We're going to talk about this very specifically here in a little bit, but we want settings. If we want things to stick around, we need to retain them. So that's why our stuff. More about that later. So we have now written programs. And I'm going to go in here and I'm going to show you. Click on the wrong thing. So double click this. So this is my machine code. And I'm going to show you. So it has stuff in the implementation. So it actually has execution code in it, whereas the other didn't. So we're going to look at our interface, and because I set everything up before to where all of my IO and everything is kind of in these global variables, I've set them all up in this table. All I have to do is say uses var global, and I have access to all of that stuff. And then in the interface, I'm going to define 3 programs. And you don't technically have to write them up there, name them in your interface. It's just, yeah, there's reasons why you may want to do that. That's like just, but not exactly sure in this in ST why you have to define it in the interface. In other languages, if you don't define it in the interface, it changes the scope, those sorts of things. Like, and that may be the case here. If you don't define the program in the interface, it keeps the scope inside of the implementation. That might be what it is. I don't know. Which means only programs inside of that implementation would have access to it. So that would be what would be called a private scope. I'm not sure if that's actually the case. Check me. If you know if that's the case, like, please comment. Like, send me nasty comments. Like, I can take them. I'm wrong every day, and that might be one of them. But so we go through and look at two things. So I've got 3 programs here. I've got a input mapping, and you don't have to do this. You can go through and define in this little address list tab thing down here over on this little side right here. You can hate yourself and define everything there. Or you can define all of your inputs, and then all you would need to do if those inputs change between machines would just change your input mapping. Say, okay, my home prox isn't on 0.1, it's on 10.1. Okay, well, I would just have to go in and change 10.1. There we go. And that's how I set up my machine. And now everything would stay exactly the same. You would just have to go and compile, and there you go. Which, by the way, I haven't been showing you that, but your compile button is up here. Here's some of the, if you were online with these codes, you actually have like, you can put in like your program status, you could put breakpoints, you could do all of that to diagnose and troubleshoot these things. But just remember, if you're breakpointing a program, depending on where it's working in the execution, stuff might not. Be careful with breakpoints is what I'm trying to say. But yeah, thinking about it, the fear that I talk about all the time is like someone that has never actually worked on industrial equipment and have only written program in like Python on a Raspberry Pi doing a project or whatever that is lighting up an LED, going in and then thinking that they can operate the same in the industrial environment as they do in the Raspberry Pi sitting on their desk at home environment. They're not the same. And so be very careful if you are entering into this world and you're saying, oh, this looks familiar. I know how to do this. I know breakpoints. I know this language. I know scope. I know all this stuff that he's talking about that all these old people don't know. Well, the old people know that if you put a breakpoint in at the wrong place, then you can literally blow the plant up. And I know that sounds crazy and dramatic and over the top, but you literally can. You can put something into a state to where it loses connection with something, and it causes some sort of catastrophic cascading failure. If you are young and in that position, that's not your fault that you're in that position. You should never be put in that position. But just know that things aren't exactly the same. I'm probably going to clip that out as a clip of, because yeah, rants like that do well on LinkedIn. But one of the things that I wanted to talk about was there's 2 different compiles. There is a compile here, accept and compile. You notice that boom hits quick, it's done. That's only compiling this block. Okay, so that's only compiling this source code. There's a save and compile over here. That compiles the whole system. and that actually goes up into TIA. It compiles up there. So know when you're writing your code and you're wanting to test, hey, is this syntax right? Is this the right thing? And you're compiling, you're using this compile up here, not over there in the corner. So right here, not over here. All right. Next thing we're going to talk about, because we've got programs, we've got axes. One of the things I guess I could write a program that's like here, like program like that. And then down here, and then start writing blah, 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 program. Right? So I write that, and oh, I've already got an error. Statement expected before in program. Oh, I guess I need to make some sort of statement in here. We're going to define a variable. It doesn't like empty programs. So let's just say I can do it here. If you'll notice, probably the thing about it is because this is in this scope, it's only going to be available to this device. This now. Oh, that's even worse. Let's see. Oh, I have to define them all in my interface. Anyway, so we're not going to do that. Wait, hold up. Telling me I can just do that and it'd be fine. I don't think so. Is it saying that's doing that? Yeah, that's not. So what apparently I have in my var global over here, right? I have in my var global a par present, and that's in an interface. So I wanted to show you, or I didn't want to show you that. Like that shows like my understanding of scopes. So I would need to pull this up into the interface like this. I mean, so Ali Reds was asking about my numeric 1 tutorial, and I mean, you can wait for all sorts of things, man. Is asking for my my numeric tutorial, and I don't know. So as I'm kind of like going through this, I'll talk about this. I did make some progress on it, but I ran into some licensing issues. So one of the things about this is the licensing that you can run on a real machine on numeric is what am I doing wrong here? Oh, because we're just going to take this and we're going to exit, and then I'm going to put it over in my var globals like this so that it actually works. All that. So the licensing for a real machine, you can't activate a trial license for a real machine, whereas you can build a virtual machine and then activate a trial license. And I've got some, I've got that machine fully set up, but I ran into some licensing issues that I'm just having trouble working through. And I went through, got it all set up, and then I ran it. Okay, I can't actually enable this machine without these licensing, and then I had to leave, and I haven't been back down to the shop since then. So now, so it'll be a minute on the Cinemeric 1 tutorial, but it is coming. We do have it. We do have a CNC machine that we've converted with Cinemeric 1. Way overkill, by the way. I spent like $1,500 on the CNC mill, and then spent like $30,000 on the Cinemeric 1 controller and hardware for it. But it's so that we could get up to speed on the Cinemeric 1 and start doing these retrofits. So it's just I haven't been down in the shop in basically a year. So it's been rough. But so we've got our program here running, and we have this program, My Servo Control, compiled, ready to go. It is now should be showing up here as a code that we can run inside of, it's a program. That means we can run it inside of an execution cycle. We can also, there is, I believe, a keyword that's like a function like that we could write code. We could write code here, and then that would be available inside that source code. It would not be available for the execution system. And so same thing that we could have with all of the other languages. Functions, programs, functions, function blocks, totally different things, and it's all different between where they get called. At this point in this, we're about to start talking about execution systems. My goodness, it's already been 2 hours. Has it really been 2 hours? Okay, I gotta go. All right, I gotta crank the BPM of the music up because we gotta cover some ground. So, the execution system in a 1500T, you kind of don't even realize that there's really an execution system there with the PLC and the kind of the 1500T, all of that stuff, regular processors. Most people don't really understand that they are organizing an execution system because they use OB1, and if they use function blocks, then they call them in OB1. Okay. Good job. Well, inside of a regular PLC, you have all of those organizational blocks, the OB blocks. OB1 is the cyclic. It's kind of just always running. It just runs all the time. Well, there are startup blocks. There are cyclic interrupt blocks. There are like MC servo, MC pre-servo. There's all these different organizational blocks that make up the execution system. You may or may not know this, like definitely go through, and again, that's in that OB, FB, FC, DB, that video that video, really go in depth into it. But inside of SIMOTION, it kind of turns it on its head. Whereas in order to execute a function block, you have to pull that block, pull that code into either some sort of organizational block. Inside of this, you don't necessarily have organizational blocks, you have an execution system. And we're going to open that up. So let's go through, and you can see here over on the left in the tree, let's open up our execution system, because it is very important to kind of understand how to kind of like run this sort of stuff, okay? Because some of these make sense, some of them do not. Some of them tie directly into stuff that is in your 1500T and your regular stuff and kind of your regular PLC. They kind of tie intuitively to it. But then there's some that don't necessarily make sense. So you have a startup task and a shutdown task. You start up, sure, that makes sense. When you go from stop to run, it executes whatever is in this stuff. And that there is an organizational block, OB, I don't know what it is. Type in chat if you know which OB the startup task is. If you put function blocks in the startup task or the startup OB, like in regular PLCs, then it only runs once. The first cycle does it, and the same thing here. When it starts up, it executes whatever that code is. If that's moving something to a proper position, if it's waiting for a timer to do whatever, it gets all the way through that function or that task. And then once that task finishes, it goes into the normal operation of the system. So inside, and this is kind of like there's a concept in like kid gloves, like the kid gloves come off, because inside of SIMOTION, you can totally do things that break everything instantly. like you could just add one line of code in and all of a sudden everything stops working. And so it sounds crazy. It's because this is more of an embedded system platform than you probably would want to be working with normally otherwise. So the startup task, you can put things called wait. There's a wait function. Any sort of like infinite while loop, like you could put an infinite while loop, like if you put a while loop in your code, put that into the startup task, and for some reason that while loop never finishes and you don't have a timeout on that while loop, then guess what? Your whole program ain't running. And some people would go in and be like, okay, I'm trying to start up, and you're going to wait for some temperature or some signal to come back from something, and you never get that signal back. Well, if you don't have a timeout that immediately comes in and throws a flag and says, hey, I timed out, this is a fault, then your operators, it'll start up. They don't realize that they didn't turn on their heater beforehand, and it's just sitting there. And they're like, oh, my machine doesn't start. So that's the startup task. Nothing else runs until the startup task finishes. Then you have the background task is kind of, but not exactly OB1. So the background task operates whenever it can. Whenever it has an opportunity, it works, which actually is OB1. Like OB1 is the background task. If it starts, the reason I say it's not quite the same, because OB1, if you interrupt OB1 too much, it's going to fault out. It's going to throw like it'll call OB81 or something like that. Or I can't remember which one. It'll call another OB. And if you don't have that OB loaded, it's just going to fault the processor out. It's just going to stop. And so if you overrun OB1, it's going to tell you. If you put stuff into the background task and then you're doing other stuff and it takes up all the time, it don't care. It just won't run the background task. Like it's not going to matter. And I might be wrong on that, but like, and again, if anything that if you're listening as a SIMOTION expert and you're listening to this and you're like, dude, Jason, you're an idiot, tell me in the comments. But the big thing is that like you could do stuff that you expect to work a certain way, and SIMOTION will just not work that way. It does not read your mind. There's no garbage collector in SIMOTION. And if you don't know what a garbage collector is, then I guess you've never used Java or C# or those languages that you can do memory allocation and then not keep up with your memory. But yeah. Anyway, so what you need to do is all of these programs need to be assigned into some sort of task. Otherwise, they don't get called. Just like a function block, if you don't put it into OB1 or you don't put it into some other function call that gets called, it doesn't ever get called. It never gets executed. Same thing here. So the background task is just whatever. It may not run. Like it literally may not run. Your motion tasks, you start them, they run through, and then they end. And then you have to trigger them again in order to actually run through. Now, inside a motion task, you can sit there and wait, and it's not going to kill anything. Because if you notice on here, it shows that these are parallel. So you can have there's a lot of them. 32 motion tasks. So, and you can start one of these and let it do its thing and wait and sit around, wait for a condition, do whatever, and then and then go through and fall through. I'm not aware of that type of function inside of regular portal or regular processor. If you know that I guess if you know of an OB that operates like a motion task, that you can have parallel ones and they can get interrupted. You can sit there and wait. It doesn't interrupt. They have a low enough priority to where they don't interrupt the background task if they're sitting there and waiting. Is basically what I'm saying. I don't think that there is that in it. If there is, please comment in chat. Please comment on the thing for this, because that's a big difference. It's a foreign concept. Motion task is. So we've got a question from Teddy. It says, in a TCPU, when using IRT, is it okay if other programming stuff runs in main? Yes, in the TCPU and in this, like background tasks normally, unless you really mess something up, like the background task is going to run. OB1 is going to run. And honestly, most of what you are doing is going to get run in main, because your cycle time on a TCPU, that cycle time that's published, that is how fast main is getting through its cycle. That has nothing to do with the servo cycle. That has nothing to do with how fast all of the drives and everything are getting updated. Like those are two separate things. And so if you have a 4 millisecond cycle time or a 10 millisecond cycle time, that means your main OB1 is running through every 10 milliseconds. And so it's totally fine to put stuff into main. The problem with SIMOTION is you are running so much other stuff natively in things that are not in main, that like, or the background task kind of has the lowest priority. And so, and if you're unfamiliar with the way interrupts work, you have a process that's running and it's trying to get through this bit of code. And it gets to here, and this code over here says, hey, I have a higher priority than you. I need to run. And it says, okay. And it goes over into this block of code, runs this, and then it goes back to wherever it left off in that lower priority, and then starts going through and says, oh, hey, I need to run over here again. And it comes back and then goes back over here. And so that's, hold up, I just lost my battery. So that is a thing that, like, the interrupt priority, it is much easier in SIMOTION to cause your background task to get really, really long. Let me change my battery real quick. little bit of a break. All right, that was much harder than it should have been. All right, let me get this back up and going. Not bad on that, guys. There we go. Should be good to go. So Ignatius, my general from the African continent general. So we got a question. So do you know how similar or different IRT over Profinet compared to EtherCAT? So it's the same concept. I mean, I'm sure there is very, very different, like a lot of different things in kind of the hardware and the stack, like the network stack level. But it's the biggest thing is that you are synchronized. And so everything on that bus makes sure that it is synchronized into the right time. And these interrupts is saying, hey, I've interrupted and I'm in sync. I'm syncing up at a certain amount of time. And so I'm always getting pulled over into this other synchronization thing. One thing about interrupts, if you aren't or if you don't have any experience with the what's it called, hardware level architecture stuff, then one of the rules of interrupts is if you're using an interrupt, get in, get out, don't mess around. That's the rule. And the reason that is if you try to do too much in an interrupt, then you're going to have a bad time. You're going to start interrupting interrupts, and then you're going to move into situations to where all right, there we go. We're going to move into a situation to where you overflow, and you're going to start making it to where that it's a possibility that your background task or your main starts to overflow, and which means if you interrupt an interrupt, you're going to have a bad time, especially if you interrupt by the same interrupt. If the same interrupt interrupts itself, you're done. It's dead. You're lost. Like literally, your process goes away because it will never complete because you're always interrupting yourself, and so it just goes off into nowhere. Oh yeah. So Lucid's talking about a couple of good questions here. Humans first gen were pretty bad. Had a lot of motion in it. Eventually changed it. The second gen. Yeah. So I still Lucid just in terms of like the first generation T processor, 15T processors, and the second gens. I still don't exactly know what those issues were, but talking about using two cyclic interrupts like in regular TIA programming. So if you have like a 100 millisecond interrupt that goes off every 100 milliseconds, and if they're the same length, try to offset them. And so like there's a phasing parameter that's set by the first what's it called, by the first scan. So it sets kind of that system time, and so it'll phase those out so that they actually get updated. The problem is if you're doing that, then your data is always one scan out. Well, with a synchronous bus, you're wanting everything to be synced up. So all synchronous buses, all of the peripheral devices gather their data and then sit and have it ready on that synchronous bus, and they have a time slot that they're taking, and that data is coming in, and on the bus they're not having to like call up the actual regular communication stack in order to, it's sitting there waiting. They just put their data into that slot. And so as that data is coming across the bus, they're just like, bloop, and it just comes in and then it gets dropped in. So that's the secret sauce behind SIMOTION and why it was so powerful, because in serial data is so obnoxiously slow if you don't have synchronization like that. And you're literally taking and queuing up all of the data on these two wires on Profibus and stacking the data. And instead of sending out all this data, it's literally taking and timing this guy to where it shoves all of its data onto the bus at exactly the time. And then by the time it gets to the processor, all of that time, that scan cycle is exactly packed and synced up, and boom, drops it into the processor. Immediately at that point, it will have this scan, this servo scan cycle, and you do all of the updating and information in that, and then bloop, and then go back and go from there. And if you're using a motion controller, the point of using a motion controller is to control motion. And so that's why most people will have like a secondary PLC for most things, kind of doing regular IO. And then it's just kind of passing back and forth like, okay, we're ready to go. You can do your motion. Cool. And then the motion processor goes around and does that. So let's talk about putting these tasks into something. So just show you real quick. So let's click on our startup task, and you can see all of our programs that we have available to us for these things. And so this is our startup task. And so I want to load. All you do is just click over. I'd already done that, but so P settings at startup. Just click. I load it into this. I say okay, and it's there. Now, say I'm going to go into motion task 1. And you sit there and say, okay, Jason, what is a motion task? What is this? Well, it might be something like, the thing about a motion task is it can be in parallel. So these can be infinite, all right? And so a way of organizing in SIMOTION is if I have like my motor control, which is my motion control, it's an MCC chart. So where is that? My motion control right here. I can use that into a task 1, because, and then I can loop that. So like if I wanted to go into this and say, put here like a while loop that is like while like this. How do I get that out? Anyway, you could put that while loop around there and just have it run infinitely. You can absolutely do that in a motion task. It's not going to kill you. It's not going to hurt you doing that. And so basically when you want to start up that motor, start it up, go through, you do that. The better way, I guess a good way of like, instead of like having an infinite like this, have some sort of like flag that says while shutdown not equals true, or while shutdown not equals true. So like while it's not in shutdown mode. And so have that, and in your startup subroutine, you set that flag to be a 0, and it doesn't ever get set until you are trying to initiate a shutdown. And then outside of that, you can do shutdown motion stuff, because there's a little bit of a difference. You saw that shutdown task. That's not yes, you can go through and gear off motors, because if you go into that shutdown task, then it's going to run through all of those things. But remember, sometimes that's not necessarily, you're not going to be powering from run into stop, right? That's the only time that task gets done. So that's a compile. I don't even know if that works, but yeah. Let's go back over here. So our execution levels. So this run to stop, that meant like your processor shouldn't be going out of or going into stop. So like on your normal shutdown of your machine, like on a Friday, you're gonna go in and you're gonna hit like stop, shut down machine, and it's gonna need to sequence out. So you can either go about it to where you're controlling those motion tasks, and those kind of like motion tasks in a motion task to where it gets activated and then goes through, and then you have a shutdown task to where it's like pulling things off, or you can have some sort of flag. But either way, those motion tasks can run, and they can sit there, and they can update, and they can do things, and it's kind of like taking and inside of OB1, you're taking a block, like a function call, that has the possibility of being only called once, and it run through once, and then it's fine. But then it can also go through every time, you know? So, but just know that they can be parallel. And then the last ones are going to be the synchronous tasks. And those are going to be the most important ones in terms of kind of what we're talking about right now. Because there's two synchronous tasks that I want to talk about. So you have a servo synchronous, which to go ahead and tell you, don't put anything in here. This is the one that has the highest interrupt priority, and if you want to Christmas tree this thing in the middle of your process, which Christmas tree means all the lights go on because everything stops working. It just goes and just wigs out. If you want to do that, jam a bunch of stuff into the servo synchronous, and at some point you're going to put enough crap in there that it's going to interrupt itself, and then it's gone. So what you should be putting things into is this IPO synchronous task. Like, for example, if you want things to update at a certain rate, no matter what, and for all of your machine data, for example, this would be comparable to kind of like your pre-servo, post-servo type things, if you're familiar with those. If you're not, don't worry about it. If you want to make a decision based on some sort of like input, output, signal, something like that, and you want to, no matter what, make sure that it's getting updated at the same rate as kind of everything else, you're going to put it into this. And so that's why we have this input mapping and then output mapping, and then we could put stuff in between it. Now, if you notice, I have multiple things, and I'm going to put in this. You notice I have multiple things, all right? Well, my servo control, I may have put that over in my motion task. I can't remember. No, that's my MCC chart. So that function, my servo control, I want to execute at a proper time. This sort of stuff, I can absolutely do this. So inputs, updates all the stuff, then I want to do the outputs. Well, the way I have this set up right now, that's not going to work that way. So what I need to do is up this in the execution order. So I want my inputs to come in, I want to do my stuff, outputs to go out. There we go. And then that's kind of, I'm guaranteeing that this stuff is getting updated every synchronous cycle. So I'm guaranteeing that it's getting updated every synchronous cycle. Now, if the servo synchronous updates, if I get too much crap in here, and my servo synchronous cycle starts to interrupt this, it's not going to crash. It's going to just cause problems to where my servo might be getting data that's not quite updated in terms of the inputs and outputs. All of the technology object stuff, that's going to be fine. It's going to know, it's going to have the encoder, it's going to have all of that information. You're going to be good. But yeah, you might not, your data might not be synchronized properly if you put too much in here. So you want to do things like that are really like low priority, like an LED light, because we're talking on the order of, say, 1 to 4 milliseconds of updating on the servo cycle. And then, all right, if it's really updating really fast, your light might be 10 milliseconds getting turned on. All right, your eye can't even perceive the difference of 10 milliseconds. So that sort of stuff should not be in your synchronous cycles. So, wow. It's 2.5 hours. Oh, goodness. How did y'all get... I thought this was going to be a quick stream, honestly, because I thought I wasn't going to be able to talk long about this stuff. So, I was wrong. I wanted to talk about how to trigger a motion task, because remember, we went through and said there is a possibility that this thing just goes through, right? It just runs once and goes out. Well, what if you wanted to re-trigger that? Because that motion task gets triggered once. Let me go through and look at this. So, I double click here and go to task configuration. If I don't check this box and I never activate that motion task and I never trigger that motion task, then it's never going to run. So if I check this checkbox and say, all right, run this task once at startup, if I don't have some sort of loop inside of that motion task, then it will run once and then fall through, and then you have to re-trigger it. I'm going to show you how to re-trigger this, because it's over here in this. So I'm here in the program execution system and the task control commands. And I want to talk about an overview. So there's a couple of different ways you can call, I think it gives an example of here, like this start task. Yeah. So this start task is, if you ran this in your ST, then it would start this task that is called by this task ID, struct task ID. And so, like, how we go through this, so start task ID starts a motion task that is in the task state stopped. So if the motion task has gone all the way through, if it's in there and it's running, then this will do nothing. If it's in the middle of a motion task, it will do nothing. It will continue to run. So if you start that task and it's in the stop, it will start that motion task, and it'll run whatever is set up in your execution system for that motion task. So I wanted to show you how this task ID is framed, because it essentially is, you're going to start typing and it'll come in, and I won't show you this, but like, So example, task, motion task 1. So you're going to have, so task as a task dot name variable, for example. So, okay. Here is how you would get task ID. So you would build this to where you're going to take this get task ID function. Let's try to do it. I didn't prepare this, and at 2.5 hours in, this might be the death of the stream. There's 16 people still here, so woohoo. So let's try to get this going. I'm gonna put this up here on. No. On all the buttons. Up here so I can actually see. All right, let's go in like my machine code and see if we can get a, so for this, we're gonna copy that. My server control. This needs to be a get. All right, so program my motion. Again, this is pure. Where's that thing? So start task ID. Where is the? Because that's not it. So where did I see that? Get task ID function. There. My gosh. See, I don't think this will compile. So I'm gonna have to do a short on this. I'm gonna have to figure that one out because I don't have time to like figure this one out. But what you would have to do is use this function properly, not like I'm using it right now. You would use this function to actually start up your motion task. So by the way, you can do this right here. Click. So that's your motion task. So that start task ID triggers a non-running motion task. And I've talked about this. There is there's like a keyword called wait for condition. Okay, that is a very specific call that can be called inside a motion task that doesn't stall out the motion task. So if you just use a regular while, then it will stall out. So like the while loop that I put in there, that probably would stall out the system. So this wait for condition makes it to where you can use this and it'll sit there and wait. And you can make it an infinite loop and it'll do it forever. But as long as that condition is good. The last thing I wanted to talk about, I haven't, because all of this stuff so far has been in SIMOTION. I want to talk about a little bit about interfacing into the overall system. What's it called? TIA portal? Yeah, like an HMI. So currently all of our variables and everything are in here. How do we get those out into TIA portal to drag and drop into our HMI, right? That was what I talked about earlier. That's the whole cool thing about the portal integration. Well, I'll show you. So we're going to click save and compile, and it's going to bring all of that information out here. It compiled, and now, and it's done. Okay. We go to SIMOTION tags, and my computer's going to die. Are you gonna click? Oh, it might be dead. It might be dead, chat. Oh, there it goes. Oh, it might be dead. I'm just gonna listen to music. I don't know, chat. It's dying a slow death. Are we dead here? Oh, it's not looking good. My fans started on. So what you would normally do is find the mouse. Which screen is the mouse on? Ooh. Okay, it's not liking this, chat, but anyway, you would go to the SIMOTION tags, and all of the tags that are kind of in those different groups, so like the source blocks, anything that we created, a tag that was inside of that, it would be available to use just as a regular tag. And hopefully, are you gonna live? Are you gonna live and show me the thing? Or yes, okay, woohoo! So we're gonna double click show all tags. Oh, it didn't like these. Why? Why didn't it like these? What? Okay. Be fine. Anyway. So, I click on this, right? I have the ability to drag and drop from here. So here's all of my tags. And there's an interesting little thing that's about this, and I want to show you this. See this crazy address that's some weird stuff, whatever? Yeah, it's crazy. Here's the thing. If I come in, all right, if I I'm going to throw an HMI in here real quick, okay? I really have to pee, by the way. No, we're not using a basic panel on a SIMOTION system. Who would do such blasphemy? Oh, this might kill it. All right. Hopes and prayers. Prayer hands in chat. Prayer hands in chat. Okay, it made it. It made it. All right. So we're gonna go through and make a screen. I'll just show this to you real quick, how you can actually use this stuff. So you have like var global. Ooh, I'm clicking way too fast. But I could go through and be like, all right, here's my home procs, and just drag this in here. And it makes that link. And so you can see the properties on this, that it is linked to that crazy address. All right. So I'm going to talk about how this is possible. And apparently it's not just straightforward. This little HMI export here is a thing that is based on something that I skipped over when I was talking about it before. But if we look at these retained variables, which you would kind of want for most of the stuff on the HMI, like your settings and stuff, you have this little setting here that says HMI export equals true. I have it commented out, all right? And I'm gonna bring this over from here back over, And I know when I turn around like that, you can see my bald spot on my head. So y'all are special, chat. Get the real me. And we're gonna go. Let's see, HMI export. Maybe I'm not gonna find this because I forgot where it is and I didn't write it down. But it talks about it in here to where um, this HMI export for any retained or non-retained variables by default, any global variable that you put into an interface is going to be exported out to an HMI. So any retained variable, any non-retained variable is going to be visible in the HMI. So think about it in your data blocks. You have that visible in HMI checkbox. That came out at the same time as this change, to where you can absolutely go through, and if you don't want, excuse me, you don't want these HMI variables or these variables to be visible in the HMI, so you don't want them to be able to be accessed, because this HMI has to use this crazy gobbledygook address. I don't exactly know why. It just does. You can change this to false, and it'll kill that address. Otherwise, by default, it will create that address. So you can create a segment inside of, here's the variables that I want exported, here's the variables I do not want exported, and you use this HMI export option. Yeah, so Ali Reza in chat is talking about the device proxy. The device proxy is available. It's the older way of doing it. And if you are doing a standalone version of SIMOTION, use the device proxy to bring it in. You export all that stuff into the device proxy, and then the device proxy has all of the tags and things there. It's pretty fun. So, and if you notice how I did this. In the SIMOTION tags, I opened it up and I clicked on like these. Remember, these are my source files. So these are ST files, and because I don't have my var global, I have those as var_global. Everything's accessible. Because I haven't flipped that to false, that HMI export, I can take these and it has that crazy address that I can use over in here, and I can just drag and drop over into it. So that's a cool thing. So I want, all right, for about 15 minutes, maybe 10 minutes, maybe, I'm going to talk a little bit about one of the things that I guess the questions that comes up. If you're familiar with the technology object method of kind of controlling these drives, you'll be like, okay, well, you said these are TCPUs. These are all the things, blah, 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 all that stuff. Well, so can I use the technology object functions, those MC power, MC reset, MC all of that stuff? Well, guess what? That's actually what you were using. Like in your functions that you were using, like for example, I deleted my crappy ladder logic because you have like a little function thing here. So my command library, these are kind of like my what is it in? It's not technology, it's instructions. My instructions tab over on the right hand side. That's the equivalent of this here. Well, technology. Let's see if we have like, there should be, where is it? Where's it found? Not common functions. These are get object, drive access, blah, 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 command, hydraulic. So if you'll notice, most of these functions that you're using are MC functions, and they are the same thing. I don't know why. Oh, here they are. So here's the PLC open blocks. So if you wanted to use the PLC open blocks, so these technology objects are specific for technology functions are specific for the SIMOTION platform. Here are the PLC open blocks, and those are the same one. Remember MC Power? Got a video on that one. MC Home, got a video on that one. And I'm just double clicking, it dumps it all in there, and then you line up all of the variables that you're using. This would not be right in a global variable, retained global variable declaration or interface section, but you could use these MC functions just the same as you do in technology objects. It's just that Siemens, when they really started wanting to be like, hey, we need to push this 1500T, we want to do that, they moved all to the PLC open function. So everything are these ISO standard functions instead of just a proportion or a portion of them. So you have here the move absolute, the move additive, move relative, move superimposition. You have all these MC functions here. Well, if you look at the technology objects in your regular TIA portal library, then it's a lot more. There are a lot more of them. So you can use the technology, and it's just kind of tying back together the fact that inherently these two things are pretty much the same idea. It's just the SIMOTION platform was really based on kind of this older technology that required very specific hardware in order to have the performance that these applications needed. Now, the technology objects and the 1500T processors are so much faster than a SIMOTION controller, because the SIMOTION controllers are based on like much slower hardware. Depending on which one, you might get up into maybe the performance level of a 1516T. So like the highest level is probably at the performance level of a 1516T, which they have 1518Ts, and those are like 4 times as fast as a 1516T. So orders of magnitude. And we did kind of a pricing structure. The performance and price is like right now, currently, they're priced kind of equal. But as that 400 or PM 400 status goes to 410, 420, 430, going on, and these controllers start getting phased out, those prices are going to start going up. Then all of a sudden, you're going to be looking to get like a quarter of the performance. You're going to have to pay 4 times the price, and it's going to be ridiculous. And so the 1500T, because of the newer technology and the newer hardware, is, if you're gonna make a new system, go with the 1500, because it's already, the performance and price is the same, and you're going into more standardized hardware, you're going into more standardized and easier to access features, and the MC functions are just a lot easier to do. Yeah, if you're coming from ST, there's going to be a little bit of conversion that you're going to have to go into SCL and do some conversions with stuff. Like there's no motion control charts, so you're going to have to do that. But yeah, so we are kind of going through right now and kind of wrapping up this stream. I'm about to go into bonus time, so don't leave if you're here. We're gonna check a little bit, but we're gonna take this bonus time, and after a week, we're going to cut it off and make it available to the members, and we're going to be doing some cool stuff. Right now, I'm just going to be reacting to the Hegamurl stream. He had some pretty cool stuff on that, but that's going to be in the bonus time. If you catch it within a week, you'll be able to have access to it for free, but otherwise, the members are going to have access to it forever. But yeah, this has been the SIMOTION stream. And I'm going to come back. Don't go anywhere if you're here live. Like, for real. Don't go anywhere. I'm going to be right back. But, yeah, if you haven't liked this video, please do. If you haven't subscribed, why not? It's free. And join the Discord. It's in the channel description below. So, y'all have a good afternoon. Don't go anywhere. Like seriously, don't go anywhere. But yeah. All right, we're back. See, I told you I was going to be back. All right, so one of the things is kind of funny. So if y'all didn't know, I think, so yeah, how far is the Delta Picker? I'll show you how far. It's this far. It's really close. The Delta Picker is getting there. This one, I don't know if you can see it. Oh, it'd be over this shoulder right here in my little 3D printer back there. It's got the replacement for this guy because this guy it was not of the quality that we will demand for this. But yeah, it's coming along. It's really good. I'm having to kind of like create a power system here because I don't have 220. And I also only have a 20 amp 120 circuit here. Yeah, so if you didn't realize, like, it's 120 in the outlets here instead of 220 like most of the world. Thanks, Obama. Or maybe, who would that have been? Probably not Jefferson. What was that name? Edison. Probably Edison. But yeah, I'm having to like kind of engineer a system. So you kind of see right back there in this little spot right there, I'm essentially making an off-grid system to where I've got a big battery that's sitting there, and I'm gonna like boost the voltage up into 220 and then like run it off of that, like single phase 220, and then that way I'm not tripping the breaker, because I have no idea if I trip a breaker in my in this, I have no idea what it would be, but or where I would go to like trip it. I would just be hosed. So I'm setting up this like power system to be able to handle it. But yeah, it's coming along. It's good. I've got probably 3 weeks at least before I get my cables for the motors. But yeah, and I should have all of the hardware to mount everything up. So probably in a couple weeks, probably about a month. Next stream, monthly stream. But yeah, so I didn't know. I saw a bunch of y'all in the chat there for his stream. But if you did not know that Hegamurl is back, now's it. And like, just so you know, he's on stream. I said I was going to react to this, and he said he would react to the react, and then I could react to the react to the react, and we could be like real streamers, and it'd be all meta and stuff. So when you're watching this, just know that like the reason I got into streaming was so that we could have that sort of style. Hegamurl is the original sit back automation streamer. He is the GOAT. So and he is back after 4 years, which is crazy. In his first stream, he was talking about like some of the annoying things that just happened, like with licensing and stuff, and like doing things the right way in terms of like with licenses is sometimes can be annoying. I fortunately have the opportunity to, I guess, have a company that makes money off of the stuff, and so I kind of could justify and write in business and stuff for licensing and everything. But he went out and on his own bought like 3,000 euro worth of software, which is crazy, just so he could do his streams again. So y'all definitely, if you didn't know, then you need to be watching that. But what I wanted to do, I wanted to react to something that was like in this, and this is my first ever react video, and like, so I don't know if I even like doing it right. but let's try and talk about this for a second, because like in his most recent stream, he custom made a PID controller, or started a PID controller. He was able to make it through a proportional controller, and I get asked all the time about PID. Watch this stream. Go back and watch his stream, because he really goes into kind of the nitty gritty of what what's actually going on and like the math. And he is building on stream a PID controller. So not how to use the cont C block or the PID complex, but I wanted to kind of watch a little segment of this. He has set up his proportional controller. He hasn't done the integral and derivative part because like it's kind of annoying to do. It's not simple at all. But he's done a really good proportional controller, and he's testing it, and he's linked it into this kind of simulation software, which if you're aware of like what that software is, like go through in chat and like what is it like, because first time I saw it, I'm like, this is pretty stinking cool, and it's linked in with PLC Sim, and it works really well. So I wanted to go through and kind of react to this but Ignatius has asked a question. When tuning a motor, should the gearbox be removed from it or not, since most motors are ordered together with the motor? So I'll talk about that after this react, because that actually ties into the fact of kind of like resonances, and the gearbox depends on what type of gearbox. Like the gearbox is going to create what's called a reflected inertia, and depending on how tight your system is absolutely going to have an effect on it. So really the final tune, it needs to be in system, and I'm going to be talking about some resonance stuff, but I want y'all to I'm going to watch this because so you can't see. Hold on, let me move over here. Wrong thing. Move out of his way, because again we're reacting to this, but this is on his stream. He's set up this PID controller, and he's talking about kind of some of the functions of how it's actually working. So I'm going to try to get this going, and I'm going to unmute this, and I'm going to play this.
This moment is very interesting. I mean, relatively speaking, interesting. But this moment, we had a little bit, and it's not in the measurement here. We cannot see it, unfortunately. But we had a little bit of a strange system reaction here. So
he had just tested it and traced a function to where he was testing a different gain value, and then you'll see here in a second, he's got a big simulated pot, and then he's going to run another simulation. But that just, I forgot to mention that.
What I will do again to emphasize on this, and this is a nice controller right now. What I will do to emphasize on this is I am going to increase this, and let's make it 50. Because I want to emphasize.
Remember, this is all P gain. It's only proportional.
I want to see the result, and I want to emphasize on it. So let's see. Critically damp water tank. Yeah, this is all completely unnecessary right now, but that's fine. So let me stop the recording. Let me delete the trace here. I should have saved them in the project. You were completely right there. Who said it? Keddy, I think. Yeah, I think I needed to save it. Yeah. But it's whatever. Did I download the program? The live stream will be available. It's all available on my channel. I never delete anything. No, I deleted something.
Why he's the goat?
Nothing that could be useful.
Always useful.
So I'm now starting my recording here again. So now let's go with the 150.
So watch this. Here it comes.
Set point here again.
It's pretty sick and awesome. First of all, the software is awesome.
Oh, Pranav. Yes, that's a good word. That's the word I'm looking for. Right. There we go.
So as it starts to fill up, it looks kind of normal. One thing to note about this, and it's kind of behind my head here, he has a flow, I think, of like, I don't know how fast it is, but there's flow coming out of this tank, and so it does have to balance out. And it's something interesting here, because when I was watching it, I was kind of halfway watching it, and when this happened, I'm like, oh, wait a second, this highlights something really cool.
Dennis, imagine my side of the story. Imagine, for fun and entertainment, I am doing a live stream.
I've never heard that before. Anybody
imagine my side of things. Oh no. But you're right. Yeah, yours is not good. Mine is worse. this is kind of a good system, though.
He starts to see
Yeah.
it.
But what you
Starts
see
to
right
build
now,
up.
right? And this is what I wanted to provoke. You control the biting point. Is it the biting point? Schleifpunkt in German. Schleifpunkt. But yeah, you're kind of controlling that. Yeah. So right now, what is happening here in the system? Oh, this is actually very good example.
So, as it's watching, if you notice, the stream is actually cutting on and cutting off. But really take a look down here at this, like at the level. And I don't know how like physics based this simulation software is, like how it's going. We'll talk about it in a second, but look how it starts to build, the waves start to build up. That's what I really want you to look at.
Do you see this? What's going on here now? What is this now? Oh no, what we have achieved is something quite terrible, and that's what I wanted to achieve. And I thought that, like, 50 is too much. Yeah, 50 is too much. We have reached an unstable point in our system. We do now have oscillations. Right? And this is so extremely important for tuning a controller right now. Right?
Yeah, so see what's going on. It started off and it was perfectly fine. Perfectly fine, and it just slowly started building and slowly started building. He's about to go to the trace here in a second. And again, this is a water system. This isn't motion, but it has very much to do with some of the topics that we've talked about before on this stream, is the fact that this is showing resonance and showing kind of harmonic components. And when he goes back to the actual trace here in a second, then absolutely. So yeah, that's kind of the thing. So Ali Reza, just pointed out the fact that he has a lot of SIMOTION tutorials in Iranian language. I did not know that. Ali Reza, can you do the auto conversion and then convert it into English? Have you tried that? Try that. Let's go back to this again, this resonant property here, because it started off and it's like completely flat, and then you could see it just slowly getting more and more and more and more and more. And let's watch it.
Imagine when he goes being in that car right now. Is there flow coming out? Yeah, I have a little bit of outflow. They're up there. Like a little bit of discharge I have, yeah. Yeah, we have oscillations going on.
I think that was actually me that asked that question.
This is oscillations. Oh no, that's bad. Let's look.
So look at this. Look at this. So this is one of the coolest things, because there is, and he mentions this like in the stream, but there is a little bit of lag in terms of the overall, I guess, between the simulation. There's a resonance, but this ties in and shows, this little graph shows resonance excitation. And we've talked about resonant frequency in mechanical systems, and especially in motion control systems, you will have some sort of spring constant, some sort of kind of stiffness of your system. And in this case, the stiffness is based on the water, but not just the water, but the diameter of that tube, how fast he's actually going in. And I don't know what it is about this particular thing. The trace itself is a timing thing, but the simulation, you see that it actually went into basically a perfect sinusoid. And what was going on there is the controller was exciting some sort of resonant frequency of that water. And you will see this to where the longer and longer he let it go, the more and more that got excited, and then the more and more it started getting stronger and stronger. And you can see this in his graph here, and it is really cool, because at first you could see, so this is the output of his controller, and let's see which one. That's the level scaled, okay? So you can see it goes up, and then it's slowly down, slowly up, slowly down, slowly up. But what's happening, I don't think he ever zooms in on this, but what's happening is the harmonic components, those waves that are going across, are starting to build up, and they'll hit. And because the gain in his system is so high, it's reacting to those little things so much and exciting that harmonic frequency further and further and further. And you'll notice at some point it just goes to where it's a pure oscillation, and you see it in that kind of like in the actual video there. Yeah, so Ignatius is commenting about Factory IO. Factory IO is the software that it is. It says it's, but in real life applications, things are completely different due to your PLC power, you getting bad values. Yeah. So, yeah, and Hegamurl absolutely brings that out, and the fact that this is not like a high-end simulation, but it still is showing what you'll see is that over time it's starting to build up. And one of the things we talk about is like the frequency domain. You have frequency components in every system. And this actually really shows it really well, because when it's exciting, that there's a small frequency component that gets excited. And the longer and longer that system is running, it starts to excite it further and further and further. And because the gain is so high, that's when it becomes unstable. And you can see it would go to a maximum. One of the things about his controller, though, is the fact that he had put in a maximum output on it, and you're dropping off. You see it's clipping off on the bottom. That means it's going to 0. And so he has a minimum. There's no way to suck the water out of his controller. And so it can only go to 0. And then I think he had it set as a maximum of like 300 or something like that. And I don't even know if it's reaching that, because it's not even having the time to build up and reach that. But you could see that it's like kind of going, oh, Ignatius, great, awesome for church. Definitely. We can watch it later. So kind of in a motion control system, what you will see in this, you could see it dramatically in the water. We were talking earlier about, what was it? It was the linear resonance. So if you have some thing that's out on, how do I do this? So if you have a length and you're moving something back here, it is going to kind of oscillate like this. And the stronger and stiffer this thing is, the less this is going to resonate. And what's going to happen is the higher frequencies are the only thing that are going to resonate, because the resonant frequency of that piece of metal is higher. Well, in this case, it has a very low frequency resonance. The water itself has a relatively low frequency resonance, because you can see that the waves aren't hitting the wall like really fast. It's not super fast. So that's why you can see it. Most of the stuff that we deal with is kind of up in the higher frequency range. And that's why if you've ever dug into an S120 controller, and the first kind of, it's a low pass filter, and it filters it off at like by default at like 1900 hertz or something like that. And that's because it's the switching frequency of the controller. And so kind of filters out all of that high stuff, because every no matter how stiff your thing is, it's going to have some sort of high frequency component to it. So let's just go ahead and filter that out, try to not excite that high frequency. And that's what this is doing. You don't want to try and change really fast. You want to limit that speed of how fast you're able to change. Unfortunately, in his system here, it's a pretty slow responding system. Let's see if there's anything else that's more about this.
This looks spicy. Look at this. Oh no.
So kind of his analysis of what's going on.
The funny uncle version of the PLC class. Oh, I mean, I'll take it as a compliment.
Oh, so
this is actually a fantastic example.
Yeah, so he said that's fantastic. So you can see here, this brown line is that wave. That's the actual feedback level, because I don't know how the factory IO, like where it's actually detecting it from. This is something you would absolutely see in your level sensor if you have a really like a point level sensor somehow, you would see it like this. And in a real tank, you're going to be measuring over something like this, or maybe like this level. Well, in a motion control system, you can more accurately measure the feedback. So you can really get into these systems well, like pretty quickly. I'm going to continue doing this because I think he goes into about what's going on and that, and I'm just going to kind of let it sit and run for a second.
Yeah, I do absolutely love this example. You see this? This is right now. My controller. It's not. I mean, it is resonance. Yeah. It is a little bit of resonance going on there. Yeah. Let's have the scaling in there. It kind of looks okay here, right? But what we start having is we do start having oscillations. How do I zoom in on just the Y layer? I can't, so it doesn't matter. So we have a little bit of an overshoot here in the beginning. How do I get there? I don't know. A plus. There's a plus icon. I'm an old man. I have to press the plus button now. So here, right? The brown one. So we go a little bit above, and then our control. Can anyone calculate how many seconds is this? I can't. Wait. 0.1 minutes in seconds.
I'm not going to call him out on this one.
This is fun. Like tuning the controller right now.
So he goes into kind of talking about
to find
the controller.
Perfect P. Right?
And kind of like the practical implications of trying to find the perfect proportional. So right now, this is only proportional gain. And we had talked before in the stream, and again, I cannot express enough. Go back and watch that stream. You got all weekend. But like he goes into like a very kind of like common topic of like, how should we be trying to tune these systems, and what's the method? And it's like, oh, in college and in university, you're going to be like in these control system class, and you're going to have like I can't even remember the root locus and Niles. He goes into a couple of different things, and like it's like all of these different ways to mathematically tune a system. Guess what? Unless your model's perfect, it's not going to win. He goes into it. So let's just watch it for a little bit more.
I would look at the difference between our oscillations here. What's the time difference? And I can see the time difference is 0.83. I mean, this is almost perfect here. Almost 0. I don't know. Maybe 0.1. Let's say 0.1 seconds. Oh no, 0.1 minutes. Can anyone calculate how many seconds is this? I can't. Wait. 0.1 minutes in seconds. 6 seconds. This is embarrassing. Yeah, this is approximately 6 seconds. Right. So approximately 6 seconds from this part. Right? Yeah. The smaller oscillations here, by the way, those are now errors in the sensor. So the smaller oscillations don't really matter right now in our case, because this is completely the simulation, and because I exaggerated with the values. So we have 6 seconds. Now with those 6 seconds, we could put this into a tuning table, right? I do have one. Oh, by chance, I do have a tuning table. Oh God. We would now, let's assume this would start happening at 25, at a P of 25. Or the P factor of a proportional gain of 25. Let's assume this would happen at this. I could test this now if we will have oscillations.
So he kind of goes through and steps through a couple of different ones to see if you have those oscillations. And it looks, and the thing about it is like, what was going on in that particular one was it building up that resonance. So one difference though in this system and a I guess some systems is that you can have overshoot in this system and it not be a problem. And when you're going through and tuning these sorts of kind of like PID controllers, what is your ultimate goal in it? kind of what is your reasonable expectations of the system. And in a motion control systems, you might need to be able to position inside of a millisecond. So you need like, if there's a disturbance, you need to get back into that speed within a millisecond. Well, obviously, you're not going to be able to do that with this controller. You're not going to be able to do this because it's just physically not stiff enough. So this is a representation of a very like weak, loose system. And so, yeah, see if there's any more. That
I know I know that I could just use AI. I was thinking about it for a second.
yeah, talking about AI.
Send the trace to ChatGPT and let it tune it. Yeah.
Have y'all done that? Have y'all done that with
no.
ChatGPT?
But I could have.
Has anybody ever tried that?
No,
I haven't.
We will not do so. My assumption is we will have oscillations now. Yeah, we have a little bit of an overshoot. No, we will not.
Yeah. So
nah. Let's say 45, 40.
That's probably. I really want to go in and show that because I told him on stream that I was going to react to this and he could react to the react. And so like this stream is mostly about the motion control side of it. And one of the things we kind of go into in some of those systems is like you may not be able to allow overshoot. And in a motion control system, most of the time it's okay to have overshoot as long as you get back down quickly. Because one of the things about a motion control system is mostly if you have a well-matched inertia system, then the motor and the load itself are going to be pretty well coupled. So like if your motor is trying to kind of turn against that, you're going to be able to bring down that overshoot quickly. And honestly, he cannot really react fast enough in that system to be able to have a really high gain and it come down. So, and with he has a pure proportional controller too, so that's unfair to him. So like he maybe challenge him on this. Like if you're watching this, Hegamurl, go through and do, when you get your integral controller, try to overshoot and then use the integral to drag it down. Because if you have overshoot, your proportional and your integral will build up pretty quick. So you're going to have have that dragging. Like if your integral is strong, the longer you have over that overshoot, not only is your proportional going to swing, your integral is going to drag it down. And so with that pure P controller, you always have that steady state error. Well, so in any motion control system, you're probably going to have some sort of integral. And what's interesting to know is I'm probably going to do a stream or something, a video about kind of the physics of motion and kind of the calculus behind it, because there are analogs for mechanically integrating. And so like inertia is kind of like integrating. It's kind of like resisting changes to certain things. And so all I have to say, in a true mechanical motion system, most of the time it's okay to have overshoot. So one of the ways that, just from a practical standpoint, that I personally will go through is check first, and this is not a all-seeing sort of system. If you can't allow overshoot for any reason, then this method doesn't work. Like you need to kind of use more of the methods that he goes through, the kind of like calculating sort of things to get you close, because you don't want to, or you just eke that proportional gain up. Because what you're going to do is you're going to get your proportional gain as high as possible, and then use your integral to reduce the steady state error. And what I mean by the proportional as high as possible is get your proportional high enough to where it doesn't resonate. And because that is going to make your system react quickly. And so it's going to be able to, any sort of disturbance, it's going to quickly be able to react. And your integral, because your integral has to build up. its power. It has to like build up over time. And even if you have a really high responsive integral gain, it takes time to build up. When you, like the servo cycle of an S120 is 125 microseconds. And so you're checking those things every 125 microseconds. You can start reacting very quickly. So tenths of milliseconds. So a quarter of a millisecond, you can react to the proportional gain can react a quarter of a millisecond. So 200, and most of the time, a really high integral gain is going to be in the order of like 250 milliseconds. And so you really want your proportional gain doing the bulk of the work, but your proportional is going to be able to like shoot you off into nowhere if you're not kind of like paying attention. So unless you have a very springy, springy, like a spring system, something that flexes a lot, you're probably not going to see the pure resonance that you saw. Like you have to really, really up the gain in order to get like a true like, and it starts to shake. There, old equipment, absolutely. Stuff that's worn out, you'll absolutely get that sort of stuff. You'll see it and it'll go, and the whole thing will just start going crazy. With most systems, you'll hear it. And so you'll hear it like, you'll hear that boo, and you'll hear kind of the response of the motor. You'll hear it like react quickly. And what it'll do is it'll sit there and overshoot and then come down and pop down like that. And so you overshoot really fast and then rip it down, and you want a couple of just pops. And so what audibly that will sound like, you'll hear like a boop, boop. It'll be like a pulse because it'll have a sound and then it'll be, and you want that to be as low as possible. When you start pushing it up in resonant frequency on these sorts of systems, you're going to hear it as just a hum. And so it's going to be like a boo sound. And if you have that, you know your gain's way too high, and you back off your gain, and you've gone too far. But yeah, so part of kind of the practical thing is push your gain as far as possible, then bring down it. Essentially what you're doing, the proportional is how fast you can react, and then your integral is how fast you can settle out. And if you have a really strong, unstable pulse, no amount of integral is really going to like be able to bring that down. So you want to find a balance of being able to react quickly to a change, but still not causing mechanical issues. Now remember, if you have an older system, I think Ignatian was talking about gearboxes. So if you have a gearbox, then any sort of higher gain is going to be more wear on mechanical components. So that's why you'll see these high performance kind of like servo motor style stuff like this Delta picker. It's going to be directly coupled to the motor. And so I fully plan on pushing this thing to failure. I'm trying to break this thing. So we're gonna mess with some stuff, and we're gonna break some stuff because it's 3D printed. You don't want to do that in the real world. So in the real world, gains will, like high gain values will increase wear on mechanical components, especially gearboxes. Ignatius asked earlier about, do you want to tune with the gearbox in session or in system? Absolutely, you have to, because it's a closed loop system. The gearbox will affect the motor. It changes the amount of reflected inertia. And if you have a standard gearbox, there's going to be a certain amount of backlash in that system. So you definitely want to do that. Cool thing about the S120 is if you do the identify controller settings with a gearbox, it will actually go through and identify any resonant frequencies based on the responses. And if you have, say, for example, a gearbox and a chain drive system, there's going to be a little bit of resonant frequency based on the springiness of that chain. And you go through and do an automatic controller setting in an S120, it'll go through and identify those, and it'll actually put in current set point filters to filter out, like notch filters, in order to filter out those resonant frequencies. But in general, the first thing is identify what your overall goal is. Then, if it is absolute performance, then your mechanical system better match it. It better be V grooves, or V belts. It better not be gearboxes. It needs to be direct coupled, shafts to mechanical components that are controlling things. It needs to be that. If it's pure performance, that's how it needs to be done. If it's accuracy and longevity, which is most of the time what most systems are, you want to find a balance between how fast that P gain is. So your P gain goes really high, but I want to bring it down for longevity. So find the perfect tune, which is as fast as possible, and then bring that P gain down and bring it down to where it's not reacting quite as fast. And so you find what's perfect and then back off, because perfect in a mechanical system is normally going to wear stuff out. But yeah, so thank y'all so much for everybody. Like, we've got, I've got to go. Honestly, I've got times to I've got a call I've got to get ready for here in a little bit. But you guys, thank you so much for this video. It's been fun. The SIMOTION SIMOTION is a great platform, and I love talking about motion control and comparing the different two. Maybe one day I know we'll be doing some more streams with that guy there. We'll definitely be working with that. And when we get the Delta Picker, we're going to be doing some pretty cool stuff. And so, yeah. Teddy, thanks you're still here. That's awesome. Thanks for joining, everybody that joined live. And if you're watching this and you're not a member, then you're probably watching it in the first week. So if you want this content in the future, this bonus section, then you gotta be a member. But otherwise, watch it on demand, or not on demand, watch it live. But yeah, thank you so much for everybody that's joined in. If you're here and you haven't subscribed, definitely subscribe. Like the video, get it out there. And we're gonna be going. I'm gonna be trying to put more content out there on a more regular scheduled basis. May not be doing these long live streams, but maybe once a month. But I am going to try to put out some content, and most of that content comes from the Discord server. So if you're not signed into the Discord server, get signed in. Be asking questions on there. You got Lucid that's on there all the time. Ignatius that's in there helping people out. Ali Reza, I see him all every now and then. We've got a lot of people that are definitely more than just me, that have expertise, that are helping people out in there. So definitely sign up for that. But yeah, if you're in the US, hopefully you're getting ready for your weekend. If you are watching this and you're not in the US, then you probably need to go to bed. Get some sleep. So yeah, take it easy. It has been great. We're going to go through and get moving. Yeah, thanks for being here, Sean. And yeah, I'll catch you next time. Until then, keep learning, and yeah, y'all take it easy.